The lake edge is shrinking. A broad sheet of water that once reached farther into the basin has pulled back, leaving a pale margin of cracked mud, trampled reeds, and the dark impressions of animals that came to drink before dawn. Beyond it, the land is neither true forest nor open desert. Patches of woodland cling to drainage lines. Grass spreads across exposed ground. Dust moves in low veils when the wind rises. The air carries the smell of dry earth, dung, bruised vegetation, and distant rain that may never arrive. Somewhere across this shifting landscape, different kinds of upright apes are moving through the same morning, following water, food, shade, and opportunity. They do not know they belong to separate branches of an evolutionary experiment. They do not know that one lineage will disappear while another will continue changing. They simply live inside a world that refuses to remain stable. To speak of 1 million years ago is to point at a moment, but the real story cannot be contained by a single date. The drama stretches backward toward roughly 2.9 million years ago, when some of the earliest known Alderaan stone tools appear, and forward toward about 900,000 years ago, when Paranthropus is fading from the record and populations of Homo erectus, or Homo ergaster, are becoming more established across wider regions. During that immense interval, Eastern and Southern Africa do not serve as a quiet stage on which one species replaces another in orderly sequence. They are crowded, dynamic worlds. Several hominin lineages overlap. Their bodies differ. Their diets overlap in some places and diverge in others. Their responses to drought, vegetation change, predators, raw materials, and seasonal abundance are not identical. Evolution here is not a ladder, it is a thicket. Before we go deeper, take a moment to like the video and subscribe, if this is the kind of history and mystery you enjoy. The mystery begins not with a missing fossil or a disputed name, but with the landscape itself. Africa during the late Pliocene and early Pleistocene is repeatedly reorganized by climate. Long-term cooling, changing rainfall patterns, tectonic activity, and shifting lake systems alter where forests persist, where grasslands expand, and where rivers continue to flow. Yet the old picture of a simple march from lush forest to open savanna is too crude. What survives in the record suggests a mosaic. Wooded patches can stand beside open grass. Wetlands make appear in one phase and retreat in another. A basin that supports abundant life for thousands of years can later become drier, saltier, or more fragmented. These changes happen at different times in different places, and the evidence remains incomplete. That instability matters because every hominin body is also an ecological wager. Strong jaws, large teeth, long legs, mobile shoulders, grasping hands, broad diets, narrow diets, familiar territories, and willingness to move all carry advantages under some conditions and costs under others. A strategy that works during decades of predictable abundance may become less reliable when rainfall becomes erratic. A feeding adaptation that seems specialized may still prove flexible across varied habitats. A lineage capable of ranging farther may find new opportunities, but movement also demands energy, knowledge, social coordination, and access to water. There is no single trait that guarantees survival. No single explanation fully accounts for why some branches endure and others vanish. The animals surrounding these hominins make the world feel both familiar and strange. Herds cross grasslands, but not always the same species that roam Africa today. Giant pigs, ancient elephants, antelopes, grazing horses, hippos, crocodiles, and large carnivores shape the risks and possibilities of daily life. Some are competitors for food. Some are sources of meat or marrow when circumstances allow. Some are immediate danger. Vultures circling above a carcass can announce opportunity from a distance, but they can also attract hyenas and big cats. Waterholes gather life into a narrow space, creating a place to drink, forage, scavenge, watch, and be watched. Even a simple walk between shade and water can pass through the territories of many other animals. The ground itself offers tools long before anyone shapes stone deliberately. Branches can probe, dig, or strike. Bone can cut or scrape under the right conditions. Sharp-edged rocks can open skin, sever tissue, crack plant material, or expose marrow. By around 2.9 million years ago, however, the archaeological record shows something more deliberate in parts of East Africa. Stones selected, struck, and reduced to produce flakes and battered implements. This does not mean that technology suddenly begins on one morning or belongs securely to one named species. The oldest known examples already sit inside a world of several hominins. At Nyanga, stone tools appear with evidence of animal processing and plant pounding, while Paranthropus teeth are found at the same site. That association is provocative, but it is not a signature. Fossils and tools found together do not identify the maker with certainty. This uncertainty changes the tone of the entire story. For much of the 20th century, it was tempting to arrange the cast into simple roles. Homo was the toolmaker, the experiment in intelligence and flexibility. Paranthropus was the powerful chewed specialist, adapted to a narrow feeding niche and eventually outmatched. New discoveries have weakened that script. Paranthropus appears earlier and across a wider range than once assumed. Its hands may have been capable of strong, controlled grips. Its diet was not necessarily as monotonous as its skull first suggested. Homo habilis, meanwhile, was not a miniature modern human waiting to become Homo erectus. Its body retained a striking mixture of primitive and derived traits. The border between ape-like and human-like becomes less a line than a blurred zone filled with overlap. Even the phrase "the first real humans" can mislead if taken literally. There is no scientific threshold at which one creature suddenly becomes fully human, while all others remain outside. The body proportions, locomotion, ecological range, tool traditions, and life history patterns associated with later Homo emerge gradually and unevenly. Homo erectus or Homo ergaster may look more familiar in some respects, especially in the legs, stride, and ability to occupy broad environments, but these features form as a mosaic. Earlier hominins may already possess parts of the package. Later populations may still retain older traits. Evolution rarely respects the clean boundaries that narration prefers. By roughly 1 million years ago, the world has changed many times over, and the survivors are not simply the strongest or the cleverest in any easy sense. Paranthropus has persisted for well over 1 million years, which is hardly the record of a failed experiment. Homo has diversified, moved, and altered its relationship with stone, food, and terrain, yet its path is not secure or uniform. In dry basins and along unstable lakes, success may depend less on one dramatic innovation than on combining many modest capacities walking farther, eating more kinds of food, using different tools for different tasks, remembering seasonal water, cooperating within groups, and adjusting behavior before a familiar landscape becomes unlivable. The old world does not announce which strategy will last. There is no final contest stage beneath the African sun. No single drought that decides the future. No moment when one lineage recognizes another as a rival. Instead, there are generations of small decisions made without foresight: where to feed, when to move, which stone to carry, which patch of woodland to revisit, which shoreline still holds water. Across hundreds of thousands of years, those decisions accumulate inside bodies, traditions, and populations, and as the climate continues to pulse between opportunity and strain, two especially distinctive hominin paths come into clearer view: Paranthropus, durable and powerful, and early Homo, variable, mobile, and not yet fully understood. The two paths do not unfold on separate continents or in neatly divided ages. They overlap across the same broad regions, sometimes for hundreds of thousands of years, and at least occasionally within the same immediate habitat. That fact alone unsettles the older picture of human evolution as a procession in which one form exits before the next arrives. After about 2 million years ago, Eastern Africa contains at least two conspicuous hominin strategies moving through the same unstable world. One belongs to Paranthropus, with its deep jaws, expanded chewing muscles, thick enamel, and skull built to withstand powerful forces. The other belongs to early Homo, a category that includes forms such as Homo habilis and, later, Homo ergaster or Homo erectus, whose bodies and behavior vary more than their names sometimes imply. Neither group represents a single fixed design. Both are internally diverse, and both survive long enough to prove that coexistence, not immediate replacement, is the central condition of this period. The most vivid evidence comes not from skulls arranged in museum cases, but from footprints pressed into wet sediment beside an ancient lake. At Kubifora in northern Kenya, tracks dating to roughly 1.5 million years ago record two distinct patterns of walking on the same surface. One set resembles the efficient heel-to-toe gait associated with Homo erectus. The other reflects a different foot structure and a somewhat different movement through the toes, consistent with Paranthropus borsei. The exact species assignments remain interpretations rather than signed identities, but the contrast is difficult to dismiss. These were not creatures separated by a geological age. They crossed the same lakeshore within a narrow window of time, perhaps hours or days apart. Their feet touched the same mud. They may have followed the same water line, watched the same herds, and navigated the same dangers. That shared ground does not prove peaceful contact, direct competition, or even awareness of one another. Fossil evidence rarely preserves behavior at that level of detail, yet it does force a more interesting question than simple replacement. How can two closely related hominin lineages occupy overlapping environments for so long without one immediately eliminating the other? The answer may lie in partial separation rather than total difference. They could have used the same landscape but emphasized different foods, different times of day, different plant patches, or different methods of extracting resources. One lineage may have depended more heavily on foods that required powerful chewing or repeated processing. Another may have ranged farther between scattered resources, scavenged more frequently, or relied more consistently on stone. But the boundaries were probably porous. Their diets could overlap. Their movements could intersect. Their hands could perform some of the same tasks. Paranthropus was not a single species frozen in one ecological role. In eastern Africa, Paranthropus boisei becomes the best-known form, while southern Africa preserves Paranthropus robustus. Earlier members of the genus extend the story farther back, and a recently described jaw from the Afar region shows that Paranthropus occupied a broader geographic range than once assumed. The fossil lies far north of many classic localities and dates to roughly 2.9 to 2.5 million years ago. This matters because wide distribution usually demands some capacity to tolerate environmental variation. A lineage confined to one narrow food and one narrow habitat would struggle to spread across such distances. The discovery does not prove unlimited flexibility, but it weakens the old image of Paranthropus as an evolutionary prisoner of a single ecological niche. Early Homo is equally resistant to simple definition. Homo habilis has often been presented as the beginning of a recognizably human line, largely because of its association with stone tools and its somewhat larger brain compared with some earlier hominins. Yet the category contains substantial anatomical variation, and scholars still debate which fossils belong together: Homo habilis, Homo rudolfensis, early African Homo erectus, and Homo ergaster are not always separated cleanly by the remains available. Teeth, jaws, skull fragments, limb bones, and isolated feet do not always tell the same story. Some specimens combine a more Homo-like face or brain case with a body that retains much older proportions. Others show more efficient terrestrial locomotion while preserving primitive features elsewhere. What appears in the fossil record is not a straight line but a patchwork. The new partial skeleton of Homo habilis from Illinois sharpens this point, dating to just over 2 million years ago. It preserves enough of the body to show that Homo habilis was not simply a smaller version of Homo erectus. Its limbs and locomotor anatomy retain a different balance of traits, some of them more primitive than the familiar image of a long-legged, wide-ranging human ancestor. This does not make Homo habilis less important. It makes the transition more gradual. The genus Homo did not begin with the complete package that later allowed populations to move across vast territories and endure harsh, open environments. Different pieces emerged at different times. Paranthropus, too, now appears more behaviorally capable than the caricature of a passive plant crusher suggests. The partial skeleton of Paranthropus boisei, known as KNM-ER 10-1000, preserves hand and foot bones alongside dental remains. Its hands show the capacity for strong grips and a degree of controlled manipulation that could have supported tool use, or perhaps even some forms of tool manufacture. Its feet confirm habitual bipedalism, although the mechanics differed from those of Homo erectus. Some features also suggest retained climbing ability, or at least a body not fully committed to the same locomotor pattern seen in later Homo. The evidence remains incomplete. An anatomical potential is not proof of a specific behavior. Still, the old division between the toolmaker and the chewer has become difficult to defend. This overlap extends into technology. Older one tools appear before the clearest fossils of Homo habilis, and in contexts where Paranthropus is also present. At Nyanga, sharp flakes and battered stones were used to process both animal tissue and plant material nearly 3 million years ago. Paranthropus teeth recovered there do not identify the maker, but they prevent easy exclusion. It is possible that early Homo made the tools. It is possible that Paranthropus did. It is possible that more than one hominin lineage participated in stone technology, using similar techniques for different purposes. The archaeological record does not yet choose among these possibilities. Coexistence, then, does not mean one sophisticated lineage standing beside one obsolete survivor. It means several hominins sharing portions of the same ecological and behavioral space while differing in degree, emphasis, anatomy, and perhaps social organization. Homo may have used stone more regularly over time, especially as Homo ergaster or Homo erectus became established. Paranthropus may have relied more heavily on its own powerful chewing system or on hand processing foods before eating them. But neither strategy was absolute. Stone did not make jaws irrelevant. Strong teeth did not eliminate the usefulness of tools. Mobility did not remove the need for familiar resource zones. The surviving evidence suggests combinations rather than opposites. For more than 1 million years, these lineages persist within a changing African world. That duration is important. A species that survives through repeated climatic shifts, volcanic events, lake expansions, droughts, and faunal turnover is not merely waiting to fail. Paranthropus was successful on evolutionary timescales. Early Homo was not guaranteed to endure. The eventual survival of one branch can make the past look inevitable. But inevitability is an illusion created by hindsight. On the lakeshore at Kubifora, both sets of footprints are equally fresh. Neither track carries a sign of destiny. One gate will eventually belong to a lineage that spreads far beyond Africa. The other will disappear. At the moment the footprints are made. However, both belong to living, adaptive beings moving through the same morning. The footprints vanish beneath later sediment, but bones endure in a different way. They survive broken, scattered, mineralized, and stripped of the movements that once gave them meaning. A jaw emerges without the rest of the face. A skull cap appears without the body. Teeth are found far from the hands that gathered food. A partial skeleton may lie close to tools, yet still refuse to reveal whether its owner made them. From such fragments, researchers have tried to reconstruct not only individual species, but the shape of the entire human family tree. The result has never been stable for long. The earliest discoveries of Paranthropus seemed almost designed to encourage dramatic categories. Its skulls were unlike those usually assigned to early Homo. The face was broad, the cheekbones flared outward, the back teeth were enormous. A crest could rise along the top of the skull in some individuals, anchoring powerful chewing muscles. The anatomy appeared so specialized that it was easy to imagine a separate and doomed experiment. A side branch adapted to crushing hard foods, while Homo moved toward intelligence, technology, and eventual dominance. Even the nickname Nutcracker Man, once widely used for Paranthropus boisei, carried the suggestion of a creature defined by one mechanical task. Yet fossils are rarely as obedient as nicknames. Microscopic wear on the teeth did not consistently match a lifetime of cracking hard objects. Chemical signatures in enamel pointed toward heavy use of C4 resources, which could include grasses, sedges, underground plant parts, or animals that consumed those plants. Different Paranthropus species also showed different dietary signals. Their jaws were clearly built to process demanding foods. But demanding does not necessarily mean hard, tough, fibrous, abrasive, or repetitive foods can reward a powerful chewing system just as much as nuts. The skull still records adaptation, but the meaning of that adaptation becomes less obvious. The genus itself has been argued over since its fossils first entered scientific debate. Some researchers have treated robust forms as members of Australopithecus, using names such as Australopithecus boisei or Australopithecus robustus. Others have retained Paranthropus as a distinct genus, emphasizing a shared suite of cranial and dental traits. Behind the terminology lies a deeper uncertainty. Did the robust species inherit their unusual chewing anatomy from one common ancestor? Or did similar features evolve more than once under comparable ecological pressures? If the traits evolved independently, the group may not represent a single clean branch. If they were inherited from a common ancestor, the genus becomes more coherent. The fossils do not settle the argument completely. Early Homo has produced even more disagreement. The name Homo habilis was introduced for fossils that seem to combine a somewhat larger brain, reduced chewing anatomy, and association with stone tools. The species name itself, meaning handy, encouraged a powerful narrative here was the creature that crossed the threshold into technology. But the original sample was fragmentary, and later discoveries widened the range of variation assigned to the species. Some skulls had larger faces, some had different tooth proportions, some appeared to hold more brain volume than others. Postcranial remains suggested a body more primitive than the skull-based story implied. Researchers began asking whether Homo habilis was one highly variable species, several species grouped together, or even a collection that crossed the boundary between Australopithecus and Homo. Homo rudolfensis added another layer. Known largely from cranial and dental remains, it has often been distinguished from Homo habilis by a broader, flatter face, larger teeth, and differences in brain case shape. Yet the sample is small, and fossils do not always preserve the features needed for confident separation. A jaw may fit one interpretation while a skull fragment supports another. Sexual dimorphism, regional variation, age, and individual difference can imitate species boundaries. Scholars still debate how much diversity early Homo truly contained, and whether the named species correspond to distinct biological populations. The problem becomes more difficult because the category Homo carries expectations. It is not merely another genus in the public imagination. It is the group to which modern humans belong, and that can tempt researchers and audiences alike to search for a decisive beginning. Brain size, hand anatomy, tool use, reduced teeth, longer legs, and dietary flexibility have all been proposed as markers of entry. None provides a clean border. Some Australopiths show capable hands. Stone tools predate the clearest Homo fossils. Early Homo bodies can retain long arms or other primitive traits. Brain size overlaps. Teeth shrink unevenly. The origin of Homo looks less like crossing a gate and more like entering a fog. New discoveries at Ledi Guraru in Ethiopia reinforce this crowded picture. Fossil teeth attributed to Homo occur there by around 2.78 million years ago, and again near 2.59 million years ago, while another form of Australopithecus remains present at approximately the same broad interval. When this evidence is considered alongside early Paranthropus, the region may have supported several hominin lineages at once. This is important because the family tree was once often drawn as a succession. One Australopith gave rise to Homo, then disappeared as its descendant took over. The newer evidence suggests branching, persistence, and overlap. Different lineages were testing different combinations of anatomy and behavior within the same changing landscapes. The recently described Afar Paranthropus jaw extends that complexity farther north and deeper in time. Its age, somewhere around 2.9 to 2.5 million years, places it near the early stages of the genus, and within the broader period when Homo also begins appearing. The distance from better-known Paranthropus sites matters as much as the date. A species or genus once imagined as geographically restricted now occupies a much larger map. This may indicate dispersal across varied habitats, a broader ecological tolerance, or simply that the fossil record has sampled its range poorly. Each possibility weakens the confidence of earlier reconstructions. The new Homo habilis partial skeleton from Ileret creates a similar disruption. Skulls had encouraged one picture, The body now complicates it. KNM ER 66461, dating to just over 2 million years ago, preserves enough postcranial anatomy to show that Homo habilis still carried a notably primitive body plan compared with Homo erectus. Its limb proportions and locomotor structure do not fit the old image of a small but essentially modern human. This is one of the most important lessons fossils repeatedly impose. A species cannot be understood from its skull alone. Evolution can alter the face, teeth, brain case, pelvis, hands, and legs at different rates. Even Homo erectus and Homo ergaster refuse perfect classification. Some researchers use Homo ergaster for earlier African populations and reserve Homo erectus for Asian forms. Others place them within a single widespread variable species. African fossils may show more graceful skulls, while later Asian specimens often develop thicker cranial bones and more pronounced ridges. But geography, time, sex, and evolutionary change blur the boundaries. The distinction can be useful for discussing regional patterns, yet it does not necessarily identify two sharply separated species. These debates are not signs that paleoanthropology has failed. They arise because the evidence is genuinely difficult. Fossilization is rare. Geological processes destroy or displace remains. Sites are unevenly distributed. A few individuals may represent populations that lasted hundreds of thousands of years. Scientists must classify species from samples that would be considered impossibly small in studies of living animals. New fossils can clarify one relationship while destabilizing 3 others. What survives in the record suggests that the family tree around 2 million to 1 million years ago was densely branched. Paranthropus was not a single-purpose relic. Homo habilis was not a finished human prototype. Homo erectus did not emerge from a clean ancestral line with every later trait already assembled. The names remain necessary, but they are labels placed over a biological reality that was more fluid, regional, and varied. Beneath those labels were populations adapting generation by generation, unaware that distant descendants would one day debate where one species ended and another began. Seen from the front, the skull of Paranthropus can appear almost architectural. The face is broad, the cheekbones flare outward, and the lower half of the skull seems reinforced for a task that mattered enough to reshape nearly every structure around the mouth. Behind the face, the jaws are deep, the back teeth are enormous. In some individuals, a raised crest runs along the top of the skull, offering additional surface for large chewing muscles to attach. Nothing about this anatomy is accidental. It is the accumulated result of countless generations in which the ability to process certain foods affected survival strongly enough to leave its mark in bone. For years. This design encouraged a simple interpretation. Paranthropus was imagined as a specialist built to crush hard objects, a creature with a skull functioning like a biological nutcracker. The nickname was memorable, and the anatomy seemed to support it. Large molars could resist wear. Thick enamel could withstand repeated stress. Broad cheekbones created room for powerful muscles. A deep jaw reduced the risk of bending under heavy force. The crest on the skull, especially pronounced in some males, suggested an extraordinary chewing apparatus. It was easy to picture these hominins seated beneath trees, cracking seeds and nuts that other animals could not open. The teeth themselves complicated that picture. Microscopic scratches and pits on tooth surfaces did not always match what researchers expected from habitual hard object feeding. Chemical evidence preserved in enamel pointed strongly toward foods linked to C4 plants in Paranthropus boisei, especially grasses, sedges, or resources growing in open environments. Yet carbon signatures do not reveal the exact menu. They cannot distinguish perfectly between eating grass blades, underground storage organs, sedge stems, seeds, or animals that had fed on those plants. The jaws show capacity. The chemistry shows broad dietary pathways. Neither provides a complete meal. A more cautious interpretation is that the skull of Paranthropus was built not for one single food, but for a range of demanding feeding conditions. Tough does not mean hard. Fibrous vegetation may require long periods of repetitive chewing. Underground plant parts can carry grit that rapidly wears teeth. Sedges can be abrasive. Seeds may vary seasonally in texture and availability. A powerful chewing system could have served as insurance, allowing Paranthropus to rely on difficult fallback foods when preferred resources became scarce. Under this model, the most impressive anatomy may reflect not what was eaten every day, but what could be eaten when the landscape offered fewer choices. That distinction matters. Evolutionary anatomy often records the hardest moments rather than the most comfortable ones. An animal may spend much of the year consuming relatively manageable foods, yet survive drought only because it can process something tougher, lower in quality, or more abundant. The massive molars of Paranthropus may therefore represent resilience rather than narrow dependence. Scholars still debate the balance between specialization and flexibility, but the old image of a creature trapped by one food is increasingly difficult to sustain. The face supports this powerful system in several ways. The cheekbones project laterally, creating space for enlarged muscles to pass toward the jaw. The front of the face is often flatter than in many earlier Australopiths, helping reposition the chewing apparatus. The jaw joint, tooth rows, and cranial base all interact to manage force. These features do not operate independently. They form a mechanical complex. When the jaw closes, stress travels through the skull, and the surrounding bone must absorb and redirect it. Paranthropus anatomy appears designed to reduce the cost of repeated loading. The back teeth dominate the mouth, while the front teeth are comparatively smaller. This imbalance suggests that food processing happened mainly toward the rear of the jaw. Instead of slicing extensively with incisors, Paranthropus may have relied more heavily on crushing and grinding. Yet even this pattern cannot reveal whether foods were first peeled, pounded, torn, or softened by hand. The mouth was only one stage in a longer chain of behavior. That chain becomes especially important in light of the newly described hand remains of Paranthropus boisei. The partial skeleton from Kenya shows hands capable of strong grasping and controlled manipulation. The fingers and thumb do not look identical to those of later Homo, but they are not clumsy instruments. They could likely hold, stabilize, pull, and perhaps strike objects with considerable force. This opens several possibilities. Paranthropus may have used sticks to dig. It may have broken plant material before chewing. It may have handled stones opportunistically, or even participated in some forms of tool production. The evidence remains incomplete, and anatomical capability is not direct proof of behavior. But the hands make one point clear: Paranthropus did not feed with its jaws alone. The feet tell a similarly complicated story. Paranthropus boisei walked upright, yet the mechanics of its stride were not exactly those of Homo erectus. The footprint evidence from Cubifora suggests differences in how weight passed through the foot and how the toes flexed during walking. Some anatomical traits may also indicate a retained ability to climb more effectively than later Homo. This does not mean Paranthropus divided its life equally between ground and trees. It means its body preserved a combination of functions that modern categories often separate too sharply. Even the dramatic sagittal crest requires careful interpretation. It is more prominent in some individuals than others and may reflect sex, body size, age, or species differences. A large crest does not necessarily mean every member of the population generated identical bite forces, nor does it mean the brain was unusually small simply because the skull looks dominated by muscle attachments. Brain size in Paranthropus remained modest compared with later Homo, but the shape of the skull exaggerates the visual contrast. The crest is best understood as part of a broader chewing system, not as a symbol of low intelligence. There is also a surprising mismatch between appearance and evolutionary success. The skull seems extreme, and extreme anatomy is often assumed to signal vulnerability. Yet Paranthropus persisted across vast spans of time and, as newer fossils suggest, across a wider geographic range than once recognized. A lineage that appears specialized from the viewpoint of modern humans may have been remarkably effective in its own ecological context. Its jaws could process foods unavailable to competitors, its teeth could tolerate heavy wear, its hands could manipulate resources, its bipedal body could move between feeding zones. Its presence across varied environments suggests that the design was not as fragile as it first appears. Still, no body plan escapes trade-offs. Large chewing muscles require energy. Massive teeth take space. A skull optimized for repeated oral processing may be less dependent on external tools, but it may also reduce the selective pressure for other ways of accessing food. If the environment changes so that difficult plant foods become less available, the anatomy cannot be redesigned within a few generations. Yet this does not mean Paranthropus was doomed from the beginning. Natural selection does not plan for distant futures. It favors what works under present conditions, and for a very long time, this system worked. The face of Paranthropus, therefore, should not be read as the face of failure. It is the face of a lineage that solved the problem of survival differently, where later Homo increasingly shifted part of food processing outside the body, using stone, transport, and perhaps more elaborate cooperation. Paranthropus carried a powerful portion of that processing machinery in its own skull, but the contrast was never absolute. Teeth and tools could coexist. Strong jaws did not prevent manipulation. A flexible hand did not require a human-like face. The anatomy preserves a strategy, not a destiny. When these skulls are viewed in silence, their strangeness can overshadow their familiarity. Yet behind the flared cheekbones were eyes scanning the same waterlines as early Homo. Beneath the crest was a brain navigating social groups, seasonal resources, and dangerous terrain. The jaw that looks so specialized belonged to an animal capable of adapting across hundreds of thousands of years. Its architecture was powerful, but the life inside it was likely more varied than bone alone can show. If Paranthropus announces itself through the powerful geometry of its face, early Homo is more difficult to recognize. Its fossils do not present one unmistakable design. They present variation. A skull may have a smaller face than an australopith, but still carry heavy brow ridges. A jaw may show reduced teeth while the body retains relatively primitive proportions. One specimen may appear long-legged and suited to efficient travel, while another preserves a different balance between arms, trunk, and lower limbs. The name Homo suggests unity, but the fossils repeatedly reveal a collection of populations moving through change at different speeds. Homo habilis stands near the center of this uncertainty. It has often been described as the first clear member of the human genus. Yet almost every word in that statement remains open to debate. Its brain was generally larger than that of many Australopiths, but not dramatically separated from them. Its face and teeth were reduced in some respects, but not uniformly. Its hands appear capable of controlled manipulation, yet such abilities were not exclusive to Homo. Its association with Older One tools once seemed decisive, but the earliest known Older One sites predate the clearest Homo habilis fossils, and tool-making can no longer be assigned confidently to one lineage alone. The new partial skeleton from Illoret makes the uncertainty more physical. K&M ER 6461, dating to just over 2 million years ago, preserves enough of the body to show a hominin that belongs within Homo, yet does not move or proportion itself like later humans. The limbs retain a mosaic of features. Some aspects suggest effective bipedal walking, while others remain unlike the long-legged, more fully terrestrial body often associated with Homo erectus. This was not a modern human reduced in size. It was a different anatomical experiment, carrying older structures into a new evolutionary context. That difference matters because the body influences nearly every aspect of survival. Limb proportions affect walking efficiency. The shape of the pelvis influences balance, birth, and muscle use. Shoulder structure changes how the arms move during climbing, carrying, reaching, or throwing. Foot anatomy influences speed and endurance across uneven ground. A body that remains partly adapted to climbing can still travel on the ground, but it may do so with different energetic costs. A body that becomes more committed to long-distance walking gains advantages in open terrain while surrendering some earlier versatility. Homo habilis therefore occupies an uncomfortable position in the story. It is clearly not simply an australopith with a larger brain, yet it also lacks the full suite of traits associated with later Homo. Its importance may lie precisely in that incompleteness. It shows that the transformation toward a more familiar human body did not happen as one event. Changes in teeth, brain case, hands, legs, and locomotion accumulated unevenly. Some populations may have developed one combination, others another. The evidence remains incomplete, but what survives suggests experimentation rather than a single advancing design. Homo rudolfensis deepens the problem. Some fossils attributed to this species have larger faces and larger teeth than expected for Homo habilis, yet they also possess cranial features that differ from robust australopiths. The best-known skull is broad-faced and relatively flat, with a brain case larger than many early Homo specimens. Whether this represents a separate species, a regional population, sexual dimorphism, or part of the natural variation within Homo habilis remains disputed. The sample is too limited for certainty, and classification often depends on which features researchers consider most important. The arrival of Homo ergaster or early African Homo erectus appears, at first glance, to bring greater clarity. The body becomes taller, the legs lengthen, the arms become relatively shorter. Walking seems more efficient over distance. The brain expands gradually. The face projects less. The teeth become smaller. The overall silhouette begins to look more familiar. Yet even here, the transition is not abrupt. Early specimens retain combinations of primitive and derived traits. Brain size overlaps with earlier Homo. Body size varies greatly. Some individuals are surprisingly small, others are tall and long-limbed. The category contains change across both geography and time. The distinction between Homo ergaster and Homo erectus remains especially contested. One approach uses Homo ergaster for earlier African fossils and Homo erectus for later Asian populations. Under this model, the African forms tend to have thinner cranial bones, somewhat different facial proportions, and a less extreme expression of the heavy ridges seen in some Asian specimens. Another approach treats them as regional expressions of one widespread species, Homo erectus, evolving over hundreds of thousands of years across enormous distances. Both approaches attempt to organize real variation, but neither produces a perfectly clean boundary. This uncertainty does not mean the differences are imaginary. African and Asian populations did not remain identical. Isolation, local environments, population size, and time would have shaped them. The difficulty lies in deciding when variation becomes great enough to justify separate species. Living species provide genetic, behavioral, and reproductive data. Fossils provide bone. A skull can show shape, but not whether its owner could produce fertile offspring with a distant population. Names become working models placed over a much more fluid biological reality. Even the familiar image of Homo erectus as a tall, long-legged traveller requires caution. Some fossils support that reconstruction strongly, especially individuals with body proportions suited to efficient terrestrial movement. Yet the species or species group spans such a long period and such a wide range that no single body can represent all populations. Early African forms, Georgian fossils from Dmanisi, later East Asian specimens, and island populations do not fit one uniform template. Homo erectus was successful partly because it was variable. The Dmanisi fossils are particularly important because they complicate the idea that only a large-brained, nearly modern-bodied hominin could leave Africa. Dating to roughly 1.8 million years ago, they show a population with relatively small brains, modest body size, and a surprising range of facial forms. Yet they lived far beyond Africa. Their presence suggests that dispersal did not require the full anatomical package once attributed to classic Homo erectus. Smaller and more primitive Homo populations may already have possessed enough mobility, social flexibility, dietary breadth, or technological skill to cross unfamiliar landscapes. This does not remove Homo erectus from its central role. Over time, populations assigned to Homo erectus or Augusta demonstrate an extraordinary geographic spread and ecological range. They appear in open grasslands, wooded environments, lake margins, volcanic landscapes, temperate regions, and eventually harsher dry settings. Their success cannot be reduced to brain size alone. Many of their brains remained far smaller than those of later humans. Nor can it be explained by one-tool tradition. Older one-like flake production continued alongside Acheulean hand axes in many places. What seems increasingly important is the ability to combine traits and behaviours rather than depend on one specialised solution. The face of early Homo reflects this gradual broadening. Compared with Paranthropus, the chewing apparatus becomes less massive. The molars shrink. The cheekbones no longer flare to support the same extraordinary muscle system. Yet reduced jaws do not automatically mean a better diet or a more intelligent species. They may reflect increased food processing outside the mouth, greater use of tools, changes in food selection, or shifts in development. The skull becomes less dominated by chewing, but that transformation unfolds over a long period. The brain case also changes, though not in a simple upward march. Average brain size increases across time, but there is overlap between species, and larger brains bring substantial energetic costs. Brain tissue demands reliable calories. A lineage cannot sustain expansion without changes elsewhere in ecology, diet, development, or social behaviour. The rise of Homo erectus may therefore reflect not merely a bigger brain, but a reorganized relationship between body, food, movement, and cooperation. That relationship remains partly hidden because fossils preserve structure more readily than behavior. A long leg suggests efficient travel but not the reason for the journey. A smaller tooth suggests altered feeding but not the exact meal. A larger brain case suggests greater neural capacity but not language, planning, or culture in any modern sense. Scholars still debate how much behavioral difference can be inferred from anatomy alone. Early Homo is therefore best understood not as one face replacing another, but as a shifting range of bodies learning to survive under new conditions. Homo habilis preserves older proportions. Homo rudolfensis complicates the boundaries. Homo ergaster and Homo erectus extend the range of form, movement, and geography. None represents a sudden arrival of fully modern humanity. Together, they show a lineage becoming increasingly capable of living beyond the limits that constrained many earlier hominins, not through one decisive transformation, but through a long accumulation of partial changes. The bodies of Paranthropus and Early Homo did not evolve against a fixed background. The land beneath them changed repeatedly, sometimes slowly enough to reshape generations and sometimes abruptly enough to alter the prospects of a single lifetime. Lakes expanded across broad basins and later withdrew. Rivers changed course. Woodlands thickened along drainage channels, then broke apart under longer dry seasons. Grasslands advanced into open ground, only to contract when rainfall patterns shifted again. The world was not moving in one direction from forest toward savanna. It was becoming more variable, more fragmented, and increasingly difficult to predict. This distinction is essential because the old image of human evolution often relied on a single environmental story. Forests retreated, grasslands opened, and upright walking, tool use, larger brains, and long-distance travel followed. The real record is less orderly. Eastern Africa contained mosaics in which wooded habitats, wetlands, bushland, grasslands, and exposed dry ground could exist within the same region. A hominin might feed beneath trees in the morning, cross open terrain by midday, and sleep near a watercourse surrounded by vegetation denser than the distant plains. Climatic trends mattered, but local geography determined how those trends were experienced. Tectonic activity added another layer of instability. The East African rift created basins, escarpments, volcanic highlands, and channels that influenced rainfall and drainage. Eruptions covered landscapes in ash, while also leaving mineral layers that would later allow scientists to date fossils and archaeological sites. Faulting could redirect rivers or create new lakes. A wetland might flourish in one part of a basin while another remained dry. Populations separated by what appears on a modern map to be a modest distance could experience very different ecological conditions. To reconstruct these lost environments, researchers study evidence far less dramatic than skulls. Fossil pollen reveals which plants grew nearby. Microscopic silica bodies formed in plant tissues can survive after the vegetation disappears. Carbon isotopes distinguish broadly between resources associated with C3 plants, common among trees and shrubs, and C4 plants, frequent in tropical grasses and sedges. Sediments preserve signs of flowing water, lake depth, erosion, drought, and volcanic disturbance. Fossil animals provide another clue. Because different species prefer different habitats, together, these traces show environments changing repeatedly rather than following one smooth transformation. For hominins, water was the most immediate limit. Food could sometimes be substituted. A scarce fruit might be replaced by roots, seeds, grasses, meat, or another plant resource. water allowed far less compromise. A shrinking lake compressed animals, predators, and hominins into the remaining wet zones. A vanished spring could make an otherwise rich feeding area unusable. Knowledge of seasonal water sources may therefore have been as important as knowledge of food. Individuals moving through the landscape needed to remember where water persisted, which channels flooded after rain, and which distant patches of vegetation signaled moisture below the surface. Lake margins offered abundance but also danger. Reeds and sedges provided plant foods, hippos, fish, turtles, birds, and other animals gathered near the water. Carcasses might become available along the shore. Fine-grained stone and cobbles could be exposed by erosion or carried by streams. Yet crocodiles waited in shallows. Large carnivores patrolled drinking places, and soft ground could restrict escape. The same environment that concentrated resources also concentrated risk. The Cubifora footprints capture this attraction to water. Two different hominins crossed the same lakeside surface because shorelines created natural corridors. They offered easier walking, access to drinking water, edible vegetation, and information. Tracks revealed which animals had passed recently. Bird activity could indicate fish or carcasses. Fresh dung showed the direction of herds. A shoreline was not merely a place on the map. It was a moving network of signals. Paranthropus boisei appears to have been especially connected to resources derived from C4 plants, but that does not mean it lived only in open grassland or ate grass in the manner of a grazing animal. Sedges often grow in wet or seasonally flooded environments. Underground storage organs may remain available when above-ground vegetation dries. Seeds and stems vary greatly in nutritional value and toughness. A powerful chewing system could exploit resources that were widespread yet difficult to process. This may have allowed Paranthropus to survive seasonal shortages that challenged less mechanically equipped feeders. Its wide distribution also suggests that it tolerated more than one narrow setting. The early Paranthropus fossil from the Afar region extends the known range far to the north of many classic sites. That distance would have included variation in rainfall, elevation, vegetation, and water availability. The discovery does not reveal whether one species occupied the entire range continuously, or whether populations moved through favourable corridors during wetter phases. It does show that the genus was not confined to one small ecological pocket. Early Homo encountered the same mosaics but may have responded differently. Smaller chewing structures suggest that at least some food processing shifted away from the jaws. Greater reliance on hands, stone, and perhaps transport could widen the range of usable foods. A sharp flake could remove flesh from a carcass or open plant material. A hammerstone could break bone or crush fibrous resources. Carrying food from one location to another could separate feeding from the place where the resource was found. None of these behaviors eliminated environmental limits, but together they may have reduced dependence on a single patch or season. Movement itself became an ecological strategy. A population capable of travelling farther could connect scattered resources across a drying landscape. Long legs and efficient walking would later become especially important in Homo erectus. But mobility did not begin all at once with that species. Earlier Homo could already disperse beyond familiar regions, as the fossils from Dmanisi eventually demonstrate. The evolutionary shift may have involved increasing degrees of movement rather than a sudden transformation from sedentary to mobile. Mobility, however, carried costs. Travelling farther required more calories. Open ground increased exposure to heat and predators. Water had to be located before dehydration became dangerous. Groups moving into unfamiliar terrain could not rely on generations of detailed local knowledge. A broader range was useful only if behavior, memory, and social cooperation could support it. The advantage of early Homo may not have been movement alone, but the ability to combine movement with flexible feeding and repeated use of technology. Paranthropus may have used a different balance. Its powerful teeth and jaws allowed more processing to occur within the body, potentially reducing dependence on reliable access to sharp stone. Strong hands could still manipulate plant foods, wood, or rock. Its locomotion was fully bipedal, even if the mechanics differed from those of Homo erectus. It may have moved effectively across familiar habitats while retaining greater climbing ability. Such a strategy could remain successful for an immense span of time, especially where wetlands, sedges, grasses, and wooded refuges persisted. The problem was not that one lineage inhabited nature while the other escaped it. Both remained bound to rainfall, vegetation, water, and other animals. The difference may have been how many ecological options each could assemble when familiar conditions broke down. Paranthropus possessed an extraordinary internal processing system. Homo increasingly added external methods: cutting, pounding, carrying, combining resources, and perhaps sharing them in more structured ways. Yet scholars still debate how consistently these behaviors were practiced and how sharply they separated the two lineages. By the later part of the story, near 1 million years ago, some Homo erectus populations were living under conditions that earlier interpretations would have considered unusually harsh. At Ngaji Nanyori in Oldupai Gorge, evidence from roughly 1.2 to 0.8 million years ago points to semi-desert or steppe desert conditions, with aridity, unstable vegetation, and limited water. Homo erectus did not merely pass through once. Archaeological traces suggest repeated occupation and continued exploitation of the area. This reveals a degree of ecological persistence that once seemed characteristic only of much later humans. The survival of Paranthropus and Homo across changing landscapes therefore depended on more than enduring heat or finding enough calories. It depended on timing. Rain could turn dry channels into temporary rivers. Plants could become edible for only a short season. Herds moved. Wetlands shifted. A lineage needed either anatomy suited to the resources that remained, or behavior flexible enough to follow what had moved elsewhere. Often, it likely needed both. Nothing in the landscape guaranteed which combination would prevail. Woodlands did not vanish everywhere. Grasslands did not expand without interruption. Water did not retreat at the same rate across Africa. The environmental record offers no single catastrophe that explains the fate of Paranthropus or the expansion of Homo. Instead, it reveals repeated tests, each slightly different from the last. Across those tests, one lineage continued to rely heavily on a remarkably durable body, while the other increasingly extended its survival strategy beyond the body and into movement, objects, and learned behavior. Long after muscles, skin, and stomachs have disappeared, teeth continue to hold traces of what passed through the mouth. Their surfaces record wear. Their enamel preserves chemical signatures formed during childhood. Tiny scratches and pits reveal how food interacted with the teeth in the final weeks or months of life. Even microscopic particles trapped in hardened deposits can sometimes hint at plants, dust, or other materials. Teeth are not complete diaries, but among the scattered remains of early hominins, they are some of the closest things the fossil record offers. For Paranthropus, those records have repeatedly challenged first impressions. The skull appears built for extreme chewing. The molars are broad, the enamel is thick, and the jaws are deep enough to resist substantial force. Such anatomy once seemed to announce a diet dominated by hard nuts, seeds, and other resistant objects. Yet when researchers examined the microscopic wear left on the tooth surfaces, the expected pattern did not consistently appear. Paranthropus boisei often lacked the heavy pitting associated with frequent hard object consumption. Its teeth looked less like those of a lifelong nutcracker than the skull's dramatic architecture suggested. This mismatch did not make the anatomy meaningless. It changed the question. Instead of asking which single hard food required such a skull, researchers began asking whether the chewing system was designed for foods that were tough, abrasive, repetitive, or seasonally difficult rather than simply hard. Fibrous stems can demand long chewing without leaving the same marks as nutshells. Underground storage organs may be coated in grit. Sedges growing near wetlands can be mechanically demanding. Dry season resources can be low in quality, yet abundant enough to sustain a population, if the mouth is capable of processing them efficiently. The chemical evidence added another surprise. Carbon isotopes in the enamel of Paranthropus boisei indicate a heavy reliance on resources associated with C4 plants. In tropical Africa, that category includes many grasses and sedges. The result made Paranthropus seem even more unusual, because most living apes rely strongly on fruits, leaves, and other C3 resources connected to trees and shrubs. Yet the isotopes reveal a broad pathway through the ecosystem, not the exact item eaten. A C4 signal could come from grass blades, sedge stems, seeds, roots, underground organs, or even animal foods derived from grazers. The chemistry narrows the field without identifying the meal. Different Paranthropus species do not tell identical dietary stories. Southern African Paranthropus robustus appears to have used a broader mixture of C3 and C4 resources, with evidence suggesting considerable variation among individuals and across time. Some teeth show wear compatible with harder foods, but not necessarily as a constant dietary foundation. This variation warns against treating the genus as one ecological machine. Paranthropus boisei in eastern Africa may have relied more heavily on C4 resources, while P. robustus occupied a somewhat different set of habitats and food webs. Their shared cranial design did not force them into identical menus. Even within one population, diets may have shifted by season. Wet periods could provide softer plants, fruits, or fresh shoots. Dry periods might push individuals toward fibrous fallback foods, seeds, underground parts, or resources concentrated near shrinking wetlands. A skull adapted to powerful chewing could become most important during the leanest months, while leaving only a limited signal in the microscopic wear of an individual that died during a more favorable season. This is one reason different methods can appear to disagree. Dental anatomy reflects evolutionary pressures over many generations. Isotopes reflect foods consumed while enamel formed. Microwear may record only the final portion of an individual's life. Early Homo presents a different but equally complicated pattern. Its back teeth generally become smaller than those of Paranthropus, and the face is less heavily reinforced for chewing. This has often been interpreted as evidence of a higher quality diet, increased meat consumption, greater food processing, or some combination of these changes. Sharp flakes could reduce the force required to tear flesh. Hammerstones could open bones. Pounding could break plant tissues. Cutting and crushing outside the mouth would reduce the mechanical work performed by teeth and jaws. Yet smaller teeth do not reveal how frequently any one behavior occurred. The Oldowan sites show that early hominins processed a broad range of materials. At Nyanga, stone tools were used on animal tissue and bone, while battered implements also appear suited to pounding plant foods. This matters because the importance of stone technology is sometimes reduced to meat. Meat may have offered concentrated calories and nutrients, but plant processing could have been equally important in daily survival. A stone used to crush a fibrous underground organ or break open a tough seed might leave fewer dramatic traces than a butchered carcass. Yet it could contribute more regularly to the diet. Cut marks and broken bones show that hominins sometimes gained access to animal tissues, but the pathway remains uncertain. They may have hunted small or vulnerable animals in some circumstances. They may have scavenged from carnivore kills. They may have claimed carcasses found near water or used stones to break bones after most flesh was gone. These strategies were not mutually exclusive. The evidence remains incomplete, and the balance between hunting and scavenging probably changed across species, environments, and time. Teeth also record dust. In open, dry landscapes, food is rarely clean. Wind-blown sediment settles on plants. Roots and tubers carry soil. Meat removed from a carcass on the ground can collect grit. Repeated exposure to abrasive particles wears enamel even when the food itself is soft. This complicates attempts to reconstruct diet from tooth damage alone. A heavily scratched surface may reflect what coated the food as much as the food's texture. The enormous molars of Paranthropus may therefore have provided more than crushing power. They also offered a large grinding surface and a long-lasting reserve of enamel. If food carried abrasive particles or demanded hours of chewing, thick enamel could extend the functional life of the teeth. Tooth failure was a serious threat in a world without cooking pots, dental care, or reliable access to soft food. A body that could continue processing rough resources into adulthood held a genuine survival advantage. Early Homo appears increasingly to have shifted some of that protective burden from anatomy to behavior. A cutting edge could divide food before chewing. Pounding could soften plant tissue. Selecting certain parts of a carcass could concentrate calories while avoiding harder material. Carrying stones or food allowed processing to occur in safer or more convenient places. Over generations, these behaviors may have reduced the need for massive teeth, but the relationship was probably circular. Slightly improved tools could make smaller jaws more viable, while changing jaws could increase dependence on processing. No preserved tooth can show whether a meal was shared, yet sharing may have transformed the meaning of food as profoundly as cutting did. A carcass, a patch of underground plants, or a cluster of seeds could provide more than one individual could consume at once. Transporting portions back to others would change the distribution of calories within a group. It could support injured individuals, nursing mothers, older adults, or companions who had spent time gathering different resources. Such behavior is difficult to prove at this early date, and scholars still debate how socially organized food transport had become. But even limited sharing would strengthen a flexible dietary strategy. Paranthropus may also have shared food or used objects to prepare it. Its hand anatomy leaves that possibility open. The contrast between the lineages should not be exaggerated into one creature chewing alone while another gathered around tools. Both lived socially, both learned from others, both likely handled food before placing it in the mouth. The difference may have been one of emphasis how often stone was used, how many foods depended on external processing, how far resources were carried, and how strongly survival relied on learned technological routines. Teeth cannot identify those routines directly, but they expose the weakness of simple labels. Paranthropus was not merely a nut-eater. Early Homo was not merely a meat-eater. One lineage did not rely only on anatomy, while the other relied only on intelligence. What their teeth remember is a world of mixed diets, seasonal pressures, abrasive landscapes, and overlapping solutions. They record not a clean division between specialist and generalist, but different ways of surviving when the same environment offered abundance one month and scarcity the next. The most revealing clue may be that both lineages endured for so long, their diets had to be broad enough, reliable enough, or adaptable enough to support hundreds of thousands of generations. Paranthropus carried a remarkable capacity to process difficult foods. Early Homo increasingly used hands and stones to expand what could be eaten and how it could be prepared. The future would favor one of these combinations, but the teeth do not reveal an obvious winner. They reveal two successful strategies operating side by side, each capable of extracting life from a demanding landscape. A sharp flake does not preserve the hand that struck it. A battered cobble does not reveal the face of the hominin that carried it. Stone can survive for millions of years, but the act that shaped it vanishes almost instantly. This imbalance is one of the central problems in the archaeology of early humans. Tools endure more often than bodies, and bodies are rarely found with enough context to identify behavior securely. The result is a record filled with objects but only occasional makers, a technological history whose authors remain partly anonymous. The earliest widely recognized Oldowan tools appear by about 2.9 million years ago. They are simple only in comparison with later technologies. Producing a useful flake requires selecting a suitable stone, understanding where to strike, controlling angle and force, and recognizing the cutting potential of the result. Not every blow succeeds. Poor stone fractures unpredictably. A strike delivered too close to the edge may crush rather than detach a flake. A blow placed too far inward may demand more force than the hand can control. Even the most basic reduction sequence involves perception, practice, and learned coordination. At Nyanga, near Lake Victoria, these early tools appear with evidence that hominins used them for more than one purpose. Some flakes cut animal tissue. Bones show signs of butchery and breakage. Other stones were battered in ways consistent with pounding plant material. The site reveals a flexible technology already applied across different food sources. It also preserves Paranthropus teeth. That association is one of the most provocative clues in the entire story, because it places a robust hominin beside an unexpectedly early technological record. Yet proximity is not authorship. The teeth may belong to individuals who never touched the tools. The makers may have been early Homo, another hominin, or several groups visiting the same place at different times. Sediments can accumulate slowly enough to combine events separated by years or generations. Water can move bones and stones. Carnivores can scatter remains. Even when fossils and artifacts lie close together, archaeology rarely offers the equivalent of a handprint on a tool. For decades, Homo habilis was treated as the natural maker of the older one. Its name reinforced the idea, and its fossils were found in regions rich in early artifacts, but the chronology no longer allows such confidence. Older one technology appears before the clearest record of Homo habilis, and the newly recognized abilities of Paranthropus hands make exclusive ownership even less defensible. Strong grips and controlled manipulation do not prove stone napping, but they remove the anatomical argument that Paranthropus could not have participated. The possibility of multiple tool-making lineages should not be surprising. Among living primates, tool use appears in more than one branch and serves different purposes. Early hominins shared hands, vision, curiosity, and the need to access difficult resources. Similar ecological problems could encourage similar behaviors independently. One lineage might have used stone mainly for plant processing. Another might have relied more often on cutting flesh or opening bone. Shared techniques could also pass through observation where groups encountered one another, although direct evidence for such transmission at this date does not survive. What has become clearer over time is not necessarily the invention of stone technology, but its increasing regularity. Early tool use may have been occasional, local, or dependent on immediate opportunities. In later to early Homo, and especially in Homo ergaster or Homo erectus, stone production appears more consistently integrated into daily survival. Suitable raw material was selected repeatedly, tools were transported, reduction strategies were maintained across occupations. The difference may have been less between tool users and non-tool users than between lineages for whom technology was useful and lineages for whom it became increasingly indispensable. The emergence of Acheulean technology after roughly 1.8 million years ago has often been presented as a decisive leap. Large cutting tools, including hand axes and cleavers, were shaped on both sides and sometimes produced with striking symmetry. Their manufacture required more extensive planning than detaching a few sharp flakes. The maker had to manage the stone as a three-dimensional volume, remove flakes in sequence, preserve useful edges, and sometimes transport large blanks or finished tools across the landscape. These objects are strongly associated with Homo erectus or Homo ergaster, and they remain one of the clearer signs of changing technological behavior, but even here, the record resists a clean revolution. Acheulean hand axes did not replace older one-like methods everywhere. Simple flakes, cores, and pounded stones remained useful for hundreds of thousands of years. At Ngaji Nanyori, between about 1.1 and 0.9 million years ago, Homo erectus populations living under dry, unstable conditions continued to rely heavily on flake-based strategies alongside larger Acheulean tools. This coexistence reveals something important about technological success. A hand axe may look more advanced, but complexity is not always efficiency. Producing one consumes time, skill, and suitable stone. A simple flake can be made quickly and may perform a cutting task just as well. A heavy-duty core can break bone or crush plant material without elaborate shaping. The advantage of Homo erectus may not have been possession of one superior tool type, but the ability to choose among several methods depending on material, location, and need. Raw stone itself shaped behavior. Volcanic rock, quartz, quartzite, chert, and other materials fracture differently. Some produce sharp, predictable flakes, others are coarse, brittle, or difficult to control. A group living near abundant high-quality stone could discard tools freely. A group moving through a region where suitable rock was rare might carry tools farther, resharpen them, or use less ideal material. Technology therefore records not only intelligence, but knowledge of geology and movement through terrain. Transport is especially revealing. A stone found far from its natural source implies memory and anticipation. It may have been carried because the group expected future cutting needs. That does not require modern planning or symbolic thought. But it does suggest that some tools had value beyond the moment of manufacture. A carried stone becomes a portable opportunity, allowing a hominin to respond to a carcass, plant patch, or emergency encountered later. Paranthropus remains difficult to place within this technological landscape. Its fossils occur near tools at several sites, but no artifact tradition can be assigned securely to it. If Paranthropus made stone tools, it may have done so less frequently or in ways archaeologists cannot distinguish from the work of Homo. If it relied more heavily on wooden implements, digging sticks, or perishable plant tools, most evidence would have disappeared. The archaeological silence may therefore reflect preservation rather than absence. The disappearance of Paranthropus offers another warning. The East African stone tool record does not show a sudden transformation at the moment the lineage fades. There is no clear technological horizon announcing that Homo has replaced a rival. Acheulean and Oldowan-like behaviours continue. Tool frequencies and strategies change gradually and unevenly. This weakens the idea that one technological breakthrough directly caused Paranthropus extinction. Stone tools reveal a growing dependence on learned behaviour, but they do not record conquest. They cannot show Homo driving Paranthropus from feeding grounds or denying it resources. They cannot demonstrate that hand axes defeated powerful jaws. No single explanation fully accounts for the different fates of the two lineages. Technology may have given Homo greater flexibility, especially when environments became unpredictable. But flexibility acts through many small advantages rather than one dramatic victory. A flake could shorten the time required to process food. A hammerstone could expose marrow. A carried core could provide edges far from the original source. A combination of simple and complex tools could help a group adjust to new resources without waiting for anatomy to change. Across generations, these modest benefits may have widened the range of environments Homo could tolerate. The unequal evidence remains. Stone survives, wood decays, tools endure, gestures vanish. Archaeologists see what was durable, not everything that mattered. Paranthropus may have possessed traditions that left almost no trace. Homo may have performed many behaviours that cannot be reconstructed from chipped rock. What the record does show is not the instant birth of technology, but a gradual deepening relationship between hominins and objects. Until some populations carried part of their survival strategy outside the body and into the landscape around them, the daily life of these hominins survives only in fragments because most ordinary actions leave nothing behind. A hand reaches for a branch, a group pauses in shade, a carcass is examined, a root is dug from damp soil, and almost all of it disappears without a trace. Stone tools, broken bones, ash, and footprints are exceptional because they preserve moments that would otherwise vanish. Yet even these clues are incomplete. They reveal what sometimes happened, not necessarily what happened most often. Meat occupies a large place in discussions of early Homo because animal tissue offers concentrated calories, fat, protein, and nutrients important to an energetically expensive body and brain. Cut marks on bones show that hominins used sharp stone to remove flesh. Percussion damage indicates that some bones were struck to expose marrow. At several sites, the location of marks suggests access to limbs and other nutritionally valuable parts rather than random contact with abandoned scraps. These traces confirm animal processing, but they do not establish a single way of acquiring carcasses. The old debate often divided early hominins into hunters or scavengers. The distinction was sharper in theory than it was likely to be in life. A group might capture a small animal, drive a vulnerable individual from cover, recover a carcass found near water, steal portions from a recent carnivore kill, or return after predators had fed. Each strategy required different levels of risk and coordination. The same population could use several of them depending on opportunity. Scavenging was not passive. Approaching a carcass meant reading the behaviour of vultures, hyenas, big cats, and other competitors. Fresh remains could offer more flesh, but they were also more likely to attract dangerous animals. An old carcass might be safer but yield mostly skin, tendons, and marrow. Hominins needed to judge whether a predator had truly left, whether others were approaching, and whether enough time remained to cut or break what could be carried away. A sharp flake was valuable, but so were attention, timing, and group awareness. Hunting also came in many forms. It did not need to resemble later organized pursuit of the large game. Small mammals, reptiles, birds, and young or injured animals could sometimes be taken with limited technology. Cooperative driving, ambush near water, throwing stones, or using wooden implements are all possible, though direct evidence is scarce. Wooden tools preserve badly, and the archaeological record may therefore underestimate behaviours that relied on branches, clubs, digging sticks, or sharpened wood. The importance of meat should not obscure the more reliable foundation of plant foods. Roots, tubers, seeds, fruits, leaves, sedges, and other vegetation were likely central to daily survival. Plant processing leaves fewer visible traces than butchery. A cut-marked bone can survive for millions of years. A crushed root disappears. This difference can make animal food seem more dominant than it was. What survives in the record suggests a mixed economy in which plants provided regular calories and animal tissue supplied valuable but less predictable rewards. Hammerstones were useful across this entire range. They could break bones, crack nuts, crush seeds, pound fibrous plants, and shape other stones. A single object might serve several purposes before being discarded. Sharp flakes could cut meat, peel tough plant surfaces, slice stems, or shape wood. The versatility of simple tools helps explain why older one-like methods persisted even after Acheulean hand axes appeared. Daily survival rewarded usefulness more than appearance. Food processing also changed where eating could happen. Without tools, a resource often had to be consumed near the place it was found. Cutting, pounding, and carrying created distance between acquisition and consumption. Portions of meat could be moved away from a dangerous carcass. Plant foods could be gathered from exposed ground and taken into shade. Stones could be carried to locations where resources were expected. This separation may have increased safety and encouraged repeated use of particular places. Archaeologists sometimes identify concentrations of tools and bones as activity areas, but such interpretations require caution. Water can collect objects. Carnivores can move bones. Groups may return to the same location over many years, creating a dense deposit from separate events. A cluster does not automatically represent a home base in the later human sense. Still, repeated occupation suggests that certain places offered enduring advantages: shade, water, raw stone, visibility, or access to animal roots. The social dimension is harder to detect but impossible to ignore. Large carcasses contain more food than one individual can consume quickly. Transporting portions may imply sharing, tolerance, or competition within a group. Plant patches can also be harvested cooperatively. Tool-making skills are learned more efficiently through observation than rediscovered by each individual. Even simple traditions require some degree of social stability, attention, and repeated contact. This does not mean early Homo lived in societies organized like those of modern humans. Language in its present form cannot be assumed. Division of labor is difficult to prove. Long-term food sharing remains debated. Yet individuals moving alone through predator-rich landscapes would face severe limits. Group living likely supported vigilance, learning, access to resources, and care during temporary weakness. The archaeological record does not preserve the emotional bonds involved, but survival itself points towards social dependence. Paranthropus must also be placed inside this practical world rather than outside it. Its powerful jaws may have reduced the need for some forms of external processing, but its hands were capable of forceful grasping and manipulation. It could likely dig, pull, carry, strip, and break food before chewing. It may have used stone or wood, though the evidence does not identify a distinct Paranthropus toolkit. A robust skull did not make behavior unnecessary. It changed the balance between what the body could process internally and what needed to be altered first. Fire is the most tempting and uncertain element. Controlled fire would have transformed food, warmth, safety, and social life. Cooking can soften plants and meat, increase access to calories, reduce chewing demands, and neutralize some toxins. Flames can deter predators, extend activity into darkness, and make cold conditions more tolerable. Because later humans depend so deeply on fire, it is easy to project that relationship far into the past. The evidence near 1 million years ago remains contested. Burned sediments, discolored stone, charred bone, and heated plant material can result from natural grass fires, volcanic activity, or accidental burning. To demonstrate control, researchers look for repeated burning in specific locations, patterns of temperature exposure, association with tools, and signs that fire was maintained rather than merely encountered. Some sites preserve intriguing evidence, but no single case has ended the debate. It is possible that Homo erectus used fire opportunistically before controlling it reliably. A natural wildfire could expose roasted animals, soften plant foods, clear vegetation, or create temporary protection. Individuals might learn to approach burned landscapes, preserve embers for a short time, or transport smouldering material without yet being able to ignite fire on demand. Control could have emerged gradually, with long periods separating occasional use from habitual dependence. This gradual model fits the broader story. Stone technology did not begin as a complete system. Mobility did not appear in one step. The body of Homo did not become modern all at once. Fire, too, may have passed through uncertain stages of attraction, exploitation, maintenance, and eventual mastery. Scholars still debate when each stage began, and the evidence remains incomplete. Daily survival therefore depended less on one revolutionary behavior than on a web of modest routines. Watching vultures, remembering water, choosing stone, testing a route, carrying food to shade, returning to a reliable place, learning where predators waited, using a sharp edge until it dulled. These actions rarely look dramatic in isolation, but repeated across generations they could transform a lineage. Homo erectus appears increasingly capable of combining such routines across wider and harsher landscapes. Paranthropus continued to rely on a body exceptionally well suited to difficult foods, while likely using its own learned behaviors and tools. Neither lineage lived by anatomy alone. Neither lived by technology alone. Their different futures emerged from how body, environment, objects, and social life were assembled day after day, long before any single moment could be recognized as a turning point. A body is not merely a shape inherited from the past. It is a budget. Every limb, muscle, tooth, organ, and gram of brain tissue demands energy, and every adaptation alters how that energy can be acquired, conserved, or spent. Paranthropus and early Homo did not simply possess different appearances, they carried different arrangements of cost and capability into the same changing world. Neither arrangement was universally superior. Each solved certain problems well and created vulnerabilities elsewhere. Paranthropus invested heavily in the machinery of feeding. Its large molars, thick enamel, deep jaws, and enlarged chewing muscles allowed repeated processing of resistant or abrasive foods. This system required substantial bone and muscle, but it also reduced dependence on external preparation. When suitable stone was absent, when food had to be consumed quickly, or when fibrous fallback resources dominated the dry season, powerful jaws remained immediately available. They could not be lost, forgotten, or broken like a tool. The feeding apparatus travelled everywhere the animal travelled. That reliability came with trade-offs. Large chewing muscles and reinforced cranial structures consumed developmental resources. The skull had to accommodate forces that shaped the face, cheekbones, and cranial attachments. Yet it would be misleading to treat this investment as wasted energy that should have gone toward a larger brain. Evolution does not move calories between anatomical accounts with conscious purpose. A powerful chewing system survived because, for many generations, it contributed enough to reproductive success to justify its cost. Early Homo gradually followed a different energetic path. The jaws and teeth became less massive, while the body and brain changed unevenly. Food processing increasingly occurred through hands, stones, transport, and perhaps eventually fire. This did not make eating cheaper in every sense. Toolmaking required time, practice, raw material, and social learning. Carrying tools and food demanded effort. A smaller chewing apparatus could become advantageous only if behavior reliably performed work that anatomy no longer handled as effectively. The brain was among the most expensive parts of this emerging arrangement. Even a modest increase in brain tissue raised the need for dependable energy. Early Homo brains remained far smaller than those of modern humans, and there was substantial overlap among species, but the long-term trend brought increasing metabolic demands. Those costs had to be supported by changes elsewhere: higher quality foods, broader diets, reduced digestive expenses, greater food sharing, more efficient movement, or some combination of these factors. No single explanation fully accounts for the shift. Body size added another layer. A larger body can travel more efficiently over distance because each step covers more ground, and the energetic cost per unit of mass may decline. Longer legs increase stride length. A narrower, more terrestrial build reduces some of the mechanical costs of walking. Greater height also improves visibility across open terrain and may help regulate heat by exposing more surface area above the hottest layer near the ground. Yet large bodies require more total food and water. They grow slowly, take longer to reach maturity, and become difficult to sustain when resources collapse. Homo erectus or Homo ergaster often displays the proportions associated with this more mobile strategy: relatively long legs, shorter arms, and a body increasingly committed to life on the ground. This stride becomes more familiar to modern eyes. Weight passes through the foot in a manner suited to efficient forward movement. Such anatomy could connect distant water sources, carcasses, stone deposits, and seasonal feeding areas. It also made wider dispersal possible, although scholars still debate how much of that capacity was already present in smaller and more primitive Homo populations. Paranthropus was also a habitual biped. It did not shuffle awkwardly behind Homo or cling helplessly to wooded refuges. The newer foot evidence suggests a distinct walking pattern, not an inability to travel. Its toes and foot mechanics may have preserved greater flexibility, while parts of the upper body could retain advantages for climbing or moving through complex vegetation. This combination may have been useful in mosaics where food was gathered both on the ground and above it. Retained climbing ability should not be dismissed as primitive baggage. Trees offered food, shade, visibility, and refuge from some predators. In broken woodland, a body capable of both terrestrial walking and effective climbing possessed options. The cost was that it might not match the long-distance efficiency of a more fully ground-adapted Homo erectus. Again, the comparison depends on the environment. Open, dry terrain rewards endurance. Wooded mosaics reward versatility. Strength is equally difficult to reduce to a simple ranking. The hand of Paranthropus boisei suggests powerful grasping, likely useful for pulling vegetation, manipulating tough foods, digging with implements, climbing, or stabilizing objects. Homo hands increasingly combined strength with precision, but the anatomical differences do not establish that one lineage was capable and the other clumsy. Both could manipulate their surroundings. The distinction may have concerned the frequency, variety, and cultural dependence of those actions rather than basic capacity. Endurance in Homo erectus is often connected to long-distance walking and, more speculatively, running. A tall body, long legs, efficient stride, and improved heat dissipation could support extended travel under warm conditions. Some researchers have proposed persistence hunting or long pursuits, but direct evidence at this early date is limited. Long-distance locomotion need not have evolved specifically for hunting. It could have helped groups move between water sources, follow migrating animals, patrol broad foraging ranges, or reach carcasses indicated by distant scavenger activity. Heat imposed severe constraints on such movement. A large active body produces internal heat, and open landscapes provide little shade. Efficient sweating, reduced body hair, altered circulation, and behavioral choices such as resting at midday may have become increasingly important. Though soft tissue leaves little fossil evidence, access to water remained essential. The same anatomy that permitted wider travel could become dangerous if groups misjudged distance or drought. Growth and development also shape the contrast. Modern humans have prolonged childhoods, slow maturation, and long periods of learning, but early Homo did not yet share this exact life history. Dental development suggests that early hominins generally matured faster than people today. Homo erectus may have extended growth and learning compared with earlier forms, though the timing remains debated. A longer developmental period allows more time to acquire complex skills, but it also lengthens dependence and raises the energetic burden on caregivers and groups. Paranthropus development is even harder to reconstruct. Its massive teeth and specialized skull did not appear fully formed at birth. They had to grow through carefully timed developmental processes. Young individuals likely learned feeding locations, social behavior, and resource handling just as other primates do. Their survival depended on more than inherited anatomy. Even a powerful adult chewing system was useless without reaching maturity, and reaching maturity required protection, nourishment, and social stability. Brain size cannot be used as a direct measure of intelligence or behavioral worth. Paranthropus had a smaller brain than later Homo, but it survived through changing environments for more than 1 million years. That persistence required memory, learning, social recognition, and flexible responses. Homo erectus possessed a larger brain on average, yet its success likely depended on organization and energy management as much as raw volume. A brain becomes useful through the body that carries it and the social world that trains it. The differences between these lineages therefore resemble alternative investments, rather than a contest between strength and intelligence. Paranthropus placed extraordinary capacity in teeth, jaws, and a versatile body. Homo increasingly placed survival in mobility, neural tissue, technology, and perhaps more elaborate cooperation. Both systems demanded calories. Both required learning. Both could fail when environmental conditions moved beyond their tolerances. Near 1 million years ago, the balance may have begun to favor the Homo arrangement more consistently. As habitats became unstable and resources shifted across greater distances, the ability to combine efficient walking, varied foods, portable tools, and learned strategies offered advantages that anatomy alone could not quickly match. But this was not because Paranthropus possessed an inferior body. Its body had succeeded across an immense period. The world changed, and the costs and benefits of each strategy changed with it. Seen together, the two lineages reveal that human evolution was never simply a march toward bigger brains and longer legs. It was a series of energetic bargains. One lineage carried powerful processing machinery in the skull. Another increasingly carried it in hands, stones, movement, and shared knowledge. For a long time, both bargains remained viable. Only across many climates and generations did their consequences begin to diverge. The widening difference between these lineages becomes clearest on the map. Paranthropus survives across a broader region than older reconstructions allowed, yet its known range remains largely African. Early Homo, by contrast, begins to appear far beyond the environments in which the genus first emerged. By roughly 1.8 million years ago, hominins are present at Dmanisi in the Caucasus. Soon afterward, populations assigned to Homo erectus appear across parts of Asia. The movement is not a single heroic migration, and it does not follow one clearly marked route. It is a slow expansion measured in generations, seasonal advances, temporary retreats, and repeated occupation of unfamiliar ground. No individual sets out to leave Africa. A group follows water, animals, edible plants, raw stone, or a corridor of tolerable climate. Its descendants move a little farther. Over centuries, a familiar range becomes a new frontier, then a homeland. Landscapes that appear distant on a modern map may have been connected by river valleys, grasslands, coastlines, and shifting ecological zones. During favorable climatic phase, resources could form chains across regions that later became dry, cold, or impassable. Dispersal depended as much on temporary opportunity as on anatomy. The fossils from Dmanisi are important because the travellers do not fit the traditional image of a fully developed Homo erectus marching outward with a large brain and modern body. They were relatively small. Their brains were modest. Their skulls varied enough that, if found at widely separated sites, some might have been assigned to different species. Their tools were largely simple flakes and cores, rather than elaborate Acheulean hand axes. Yet they reached a landscape far beyond tropical Africa, and survived there long enough to leave several individuals in the record. This evidence weakens the old argument that migration required a complete package of long legs, large brains, advanced tools, and sophisticated hunting. Those traits may have improved later dispersal, but movement began before all of them were fully established. Smaller and more primitive Homo populations already possessed enough behavioral flexibility to enter new environments. They may have followed grazing animals, exploited carcasses, gathered familiar plant foods along ecological corridors, and adjusted gradually to seasonal cold. The evidence remains incomplete, but their presence proves that the threshold for dispersal was lower than once imagined. Leaving a familiar region created problems that teeth and legs alone could not solve. Plants changed. Rainfall arrived at different times. Predator communities differed. Stones suitable for flaking could become scarce or unfamiliar. Water froze or disappeared seasonally in some regions. A group needed to recognize new resources without losing the ability to use old ones. Knowledge could no longer depend entirely on a landscape remembered over many generations. Flexibility itself became a survival skill. Technology helped, but not because one tool unlocked an entire continent. Simple flakes could be produced from many kinds of stone and used for varied tasks. Hammerstones could crush plants or bone. Tools could be made quickly where raw material was abundant and carried where it was not. A portable cutting edge reduced the need to evolve a new tooth or jaw for every unfamiliar food. The same basic principles could travel with a population even when the local species of animal and plant changed. Dietary breadth was equally important. A hominin dependent on one narrow resource would be vulnerable when moving beyond the ecological zone that produced it. Early Homo appears increasingly capable of combining plant foods, animal tissue, marrow, and seasonally available resources. This does not mean every population ate the same things or that meat alone drove expansion. It means the feeding strategy could be rearranged. Where fruit was scarce, roots or seeds might matter more. Where large carcasses were unavailable, smaller animals or plant foods could sustain a group. Flexibility often works through substitution rather than abundance. Social learning made that substitution more reliable. A useful stone source, a safe crossing, a plant requiring careful processing, or the seasonal path of animals could be learned and transmitted. No language like that of modern humans needs to be assumed. Observation, imitation, gesture, repeated travel, and tolerance within groups may have been enough to maintain practical traditions. As populations moved into more seasonal environments, the cost of losing such knowledge would have increased. Homo erectus later expanded this pattern across an extraordinary range. Fossils and tools associated with the species appear from Africa through western and eastern Eurasia, and into Southeast Asia. The exact timing and routes remain debated, partly because dates are revised and species assignments remain uncertain. Some populations may represent repeated dispersals rather than one continuous wave. Others may have become isolated for long periods. What looks like one broad migration on a map was probably a series of expansions, contractions, and regional experiments. Paranthropus presents the opposite geographical puzzle. New discoveries show that it was not confined to a small corner of East Africa. Its presence in the Afar region demonstrates a northern range extending far beyond many classic fossil sites. Southern African Paranthropus occupied different environments from eastern P. boisei. The genus was therefore capable of geographic and ecological variation. Yet no secure Paranthropus fossils have been identified outside Africa. Several explanations are possible, and none is complete. The most obvious concerns diet. Even a flexible Paranthropus may have remained strongly tied to plant communities, wetland resources, or climatic conditions more common in African environments. Its powerful jaws could process difficult foods, but the correct food still had to exist. Moving into more seasonal or colder regions might have reduced the availability of the resources on which its feeding system worked best. Locomotion may also have mattered. Paranthropus was bipedal and capable of travel, but its body appears less committed to efficient long-distance terrestrial movement than that of Homo erectus. Greater climbing ability and flexible feet could be advantageous in wooded mosaics, while offering less benefit across broad open corridors. A slightly higher energetic cost of walking would not prevent local movement, but over many generations it could limit how rapidly populations expanded between distant water and feeding zones. Technology may have widened the gap further if Paranthropus used stone only occasionally, or relied more heavily on perishable tools and its own chewing anatomy. Unfamiliar environments could impose greater constraints. Homo increasingly carried adaptable processing methods into new regions. A flake made from local stone could compensate for changes in food texture. A transported tool could provide access to carcasses far from raw material. Paranthropus may have been capable of such behavior without depending on it to the same degree, and dependence can drive refinement. Population structure may be just as important as anatomy. A lineage made up of smaller, more isolated populations would expand less easily and recover more slowly from local losses. Homo groups ranging widely may have maintained broader networks or recolonized empty habitats more effectively. The fossil record cannot reveal exact population sizes, mating patterns, or social connections, but dispersal is never merely an individual ability. A species expands when enough groups survive, reproduce, and remain connected across generations. There is also a preservation problem. Paranthropus may have occupied regions where fossils have not yet been found or recognized. Teeth and jaws outside known areas could be misclassified, destroyed, or buried beyond reach. Absence from the current record is not absolute proof of absence from every neighbouring landscape. Still, after decades of discovery across Eurasia, the contrast remains significant. Homo appears repeatedly beyond Africa. Paranthropus does not. The difference should not be turned into a story of courage versus limitation. Paranthropus did not fail to explore because it lacked curiosity, and Homo did not migrate because it imagined distant continents. Expansion emerged from ecological pressure, population growth, mobility, diet, social learning, and chance. A corridor opened. A drought pushed groups outward. A river valley remained productive. A population survived one winter or one dry season farther from its ancestral range than those before it. By 1 million years ago, Homo erectus had become not merely an African hominin with a wider territory, but a lineage capable of persisting across environments that differed profoundly from one another. Paranthropus remained successful within Africa, but increasingly absent from the expanding human map. The contrast was gradual, almost invisible at the scale of one lifetime. One lineage continued to refine survival within familiar ecological systems. The other carried a more portable combination of movement, tools, diet, and learned behavior into places where familiarity could no longer be assumed. Competition is easy to imagine because the two lineages shared so much. They walked through some of the same basins, approached the same water, encountered the same carcasses, used overlapping plant zones, and at least occasionally occupied the same shoreline within a narrow span of time. Yet direct competition is far more difficult to prove than coexistence. Fossils can place species in the same region. Footprints can place them on the same surface. Teeth can reveal overlapping diets. None of these clues shows one group driving another away. The old story often assumed a contest between biological power and behavioral flexibility. Paranthropus possessed the stronger jaws but the narrower strategy. Homo possessed tools, larger brains, broader diets, and eventually won. The appeal of this model lies in its simplicity. It transforms a complicated ecological history into a recognizable struggle between two designs. But the evidence does not reveal a single contest, a decisive encounter, or even a consistent pattern of replacement. Both lineages survived together for an immense period, which suggests that their relationship was not one of constant direct exclusion. Species can share a landscape by dividing it in subtle ways. They may rely on different foods within the same habitat. They may feed at different times. They may choose different parts of a wetland, woodland edge, or open plain. They may process the same resource differently or depend on it during different seasons. Ecologists call this niche partitioning, but in practice it can involve dozens of small distinctions rather than one clear separation. Paranthropus boisei appears to have relied heavily on C4 resources, perhaps including sedges, grasses, underground plant parts, seeds, or other foods connected to open and wetland environments. Early Homo likely consumed a broader mixture of plants and animal tissues, though the exact balance varied by place and time. If Paranthropus could efficiently process fibrous or abrasive resources that Homo used only reluctantly, then the two groups may have reduced direct competition even while feeding within the same general zone. Fallback foods are especially important. During favourable seasons, different hominins may have converged on desirable resources such as fruit, tender vegetation, or easily acquired animal tissue. During shortages, their strategies could separate. Paranthropus may have relied more heavily on foods that rewarded large teeth and powerful jaws. Homo may have increased transport, scavenging, stone use, or movement between patches. The foods consumed during scarcity often shape survival more strongly than those eaten during abundance. This does not mean competition was absent. Water, shade, safe sleeping locations, raw stone, and productive feeding grounds could all become limited. A shrinking lake concentrates many species into a smaller area. A drought shortens the distance between groups that might otherwise remain apart. If both lineages sought the same wetland plants, carcasses, or water access, encounters could occur. Yet the archaeological record cannot reveal whether those encounters involved avoidance, tolerance, threat, or simple indifference. The footprints at Kubifora capture the problem perfectly. Two kinds of hominin crossed the same lakeside ground. One may have arrived only hours after the other. That surface proves ecological overlap with extraordinary immediacy, but it does not show interaction. The second group may have followed the first, avoided it, failed to notice it, or recognized only old tracks in the mud. The scene is vivid precisely because its meaning remains unresolved. Body size and social organization may have influenced these encounters. A larger group could defend a carcass or water access more effectively. A more mobile group could avoid conflict by moving elsewhere. A lineage with a broad diet might surrender one resource and substitute another. A lineage more dependent on a particular wetland zone might have fewer alternatives. Yet group size, dominance patterns, communication, and territorial behavior leave little direct evidence. Competition also occurred through other animals. Hominins did not face only one another. They competed with hyenas for carcasses, with pigs and baboons for plant foods, with grazing mammals for C4 resources, and with predators for access to safe water. In some cases, these non-hominin competitors may have mattered more than the presence of another upright ape. A change in herbivore communities could reduce plant availability. A new carnivore pressure could make certain feeding areas dangerous. Ecological competition is a network, not a duel. The changing distribution of C4 grasslands near the later history of Paranthropus boisei may have intensified these pressures. Research suggests that the period surrounding its disappearance did not simply involve endless grassland expansion. In some regions, temporary increases in C3 vegetation and woody cover may have reduced particular C4 resources. If Paranthropus relied strongly on certain sedges, grasses, or underground plant parts, those shifts could have compressed its feeding opportunities. At the same time, Other grazing animals may have competed for the remaining resources. Homo may have benefited not by taking one food away, but by avoiding dependence on any single food pathway. When plant communities changed, groups could increase animal processing, move toward other water sources, rely on different plants, or adjust their technology. That flexibility would not make them immune to famine or local extinction. It would simply provide more possible responses before a population reached its limits. Technology may have altered competition indirectly. Sharp flakes and hammerstones allowed Homo to extract calories from carcasses and plants that would otherwise be difficult to use. Carrying tools increased the number of places where such processing could occur. Acheulean and Oldowan-like strategies offered different responses to different tasks. The technological advantage was cumulative rather than absolute. A hand axe did not defeat a jaw. A portable toolkit reduced the number of situations in which one anatomy alone determined access to food. Paranthropus may also have used tools, which makes the contrast less dramatic. Its hands were capable of strong grasping and controlled manipulation. It may have used sticks, stones, or other implements for digging and food preparation. What remains uncertain is whether these behaviors became as frequent, varied, and culturally dependent as they appear to have become in Homo. Capability and reliance are not the same. A lineage can perform a behavior without organizing much of its survival around it. Population density could have shifted the balance. Homo groups able to occupy more varied habitats may have expanded into regions during favorable periods and remained connected across broader networks. Paranthropus populations may have become more fragmented when preferred environments contracted. Small, isolated populations are vulnerable even without direct conflict. A few failed breeding seasons, local droughts, diseases, or barriers to movement can produce losses that larger networks absorb more easily. This possibility changes the meaning of competition. Homo did not need to attack or deliberately exclude Paranthropus. It could affect the ecological landscape simply by becoming more numerous, more widespread, or more efficient at using overlapping resources. Even then, the effect would be difficult to separate from climate, vegetation, and other animals. No single explanation fully accounts for the disappearance. The stone tool record provides no sign of a technological victory coinciding neatly with the final Paranthropus fossils. There is no sudden explosion of artifacts at the moment one lineage vanishes. There is no clear archaeological layer in which a new Homo technology arrives and Paranthropus immediately disappears. Instead, technological change continues gradually. Simple flakes remain important. Acheulean tools spread unevenly. The last appearance of Paranthropus varies by region and depends partly on how fossils are classified. The very idea of a winner also distorts the deeper history. Paranthropus survived for more than 1 million years across changing African environments. Homo suffered local extinctions, fragmented into populations, and produced branches that also vanished. The line leading eventually toward modern humans was never secure. Survival at one date does not prove superiority across all conditions. It proves only that a particular combination of traits, behaviors, population structures, and chance remained viable. Near the end of their coexistence, the balance may have shifted increasingly toward Homo. Wider mobility, broader diets, technological versatility, and the ability to occupy dry environments offered protection against ecological instability. Paranthropus may have retained fewer options when certain plant communities contracted, or when populations became isolated. But even this conclusion must remain probabilistic. The evidence suggests differences in resilience, not a documented final contest. Across the lakeshores and grassland mosaics, the two lineages continue to encounter the same changing world. They may have watched one another from a distance. They may have crossed old tracks, shared water on different days, or fed within sight of the same herds. Their relationship was likely a shifting mixture of overlap, separation, avoidance, and indirect competition. One branch would ultimately disappear, but the record preserves no clear victor standing over the last survivor. It preserves only two strategies exposed to the same unstable climate, with one gradually losing the ecological space it needed to continue. Extinction rarely leaves a final scene. There is no known site where the last Paranthropus collapses beneath a changing sky, while Homo watches from the distance. There is no fossil layer that marks a clean ending across the continent. Instead, the lineage becomes less visible. Remains grow younger, then rarer. Dates vary by region. Some fossils are difficult to classify. Eventually, after surviving for more than 1 million years, Paranthropus no longer appears in the record. In eastern Africa, the final well-supported appearances are often placed around 1.3 million years ago, although proposed younger remains and differences in classification keep the boundary uncertain. In southern Africa, Paranthropus robustus may persist somewhat later, perhaps toward 1 million years ago or beyond, depending on the site and dating method. These endings need not represent one extinction event. Separated populations may have declined at different times under different local pressures. A genus spread across large parts of Africa could disappear region by region, leaving no single date that applies everywhere. The easiest explanation has long been overspecialization. Paranthropus possessed extraordinary jaws and teeth, so the argument followed that it depended on a narrow diet. When the environment changed, its preferred food vanished, and the lineage could not adjust. This story is tidy, memorable, and no longer sufficient. The wide geographic distribution of early Paranthropus, the variation between species, the chemical evidence for different dietary pathways, and the newly recognized capabilities of its hands all show a more versatile animal than the old caricature allowed. A lineage that survived repeated climatic fluctuations over such a long period cannot reasonably be described as inflexible in every sense. Yet rejecting the simplest version of specialization does not mean diet was irrelevant. Paranthropus boisei appears to have relied heavily on C4-derived resources, even if those resources included several kinds of grasses, sedges, seeds, stems, and underground plant parts. Dependence on a broad category can still create vulnerability when ecosystems reorganize. A feeding strategy may be flexible within one range of habitats and fragile outside it. The question is not whether Paranthropus ate only one food, but whether enough of its reliable foods remained available as rainfall, vegetation, and water systems changed. Research on Eastern African vegetation around the later history of boisei suggests that the critical period was not simply a time of expanding open grassland. In some areas, C4 grasslands contracted while woody C3 vegetation increased temporarily. Such changes could have reduced particular plants associated with open or wetland environments. Sedges may have declined as lakes and marshes shifted. Underground resources could have become less predictable. At the same time, grazing animals may have competed more intensely for what remained. The large chewing apparatus would still allow Paranthropus to process mechanically difficult foods, but anatomy cannot create calories where suitable plants no longer grow. A powerful jaw protects against toughness, not disappearance. If resource patches became smaller and farther apart, locomotion and ranging behavior would become more important. If wetlands dried or moved, populations accustomed to those productive margins might need to travel greater distances or cross more exposed terrain. Even a modest disadvantage in mobility could matter when repeated across generations. Climate instability may have amplified these problems without acting as one direct cause. African climates during the Pleistocene fluctuated across several timescales. Long-term drying trends were interrupted by wetter intervals. Lakes expanded and contracted. Local rainfall patterns responded to global climate cycles, regional topography, and tectonic change. One basin could remain productive while another deteriorated. Populations might survive several difficult phases and then fail during a later combination of drought, vegetation change, and isolation. This makes extinction less like a single blow and more like the loss of recovery opportunities. A local population declines when food becomes scarce. Under favorable conditions, migrants from another region could replace it. But if habitats become fragmented and surrounding populations are also shrinking, recolonization becomes less likely. Each local loss leaves a larger gap. Over time, the network breaks apart. Population size is almost invisible in the fossil record, yet it may be central to the disappearance. A species can remain anatomically effective while becoming demographically fragile. Small populations suffer from chance fluctuations in births and deaths. They recover slowly after drought or disease. They may lose useful traditions or struggle to find mates across fragmented ranges. Reduced genetic diversity can further weaken resilience. Although no Paranthropus DNA has survived to reveal whether this occurred, the fossil record itself may exaggerate suddenness. The youngest fossil found is rarely the final individual that lived. Paleontologists call this the senior lips effect because preservation is incomplete. A lineage's apparent last appearance usually predates its actual extinction. Paranthropus populations may have survived for thousands or tens of thousands of years beyond the youngest currently known fossils. They may also have occupied regions where sediments did not preserve bone or where sites remain undiscovered. The final phase was probably longer and more geographically uneven than the record suggests. Could Homo have contributed? Almost certainly in some indirect way, but the extent remains uncertain. Homo erectus or Homo ergaster increasingly occupied a wide range of habitats, used stone regularly, processed diverse foods, and moved across greater distances. If both lineages depended on overlapping water sources, plant zones, or animal resources, expanding Homo populations could have added pressure. Greater flexibility might have allowed Homo to remain in landscapes where Paranthropus populations were already stressed. Yet there is no evidence of a technological invasion that immediately removes Paranthropus. Stone tool records do not show a sudden shift at the time the genus disappears. Acheulean tools had existed long before the final fossils, and simple flake technologies continued afterward. If Homo contributed to the extinction, it probably did so through long-term ecological overlap, population expansion, and more efficient use of changing resources rather than direct conflict or one decisive invention. Predators and disease may also have mattered, though evidence is scarce. Fragmented populations can become more vulnerable to predation because they must travel farther between safe habitats. Changing animal communities may introduce new risks. Diseases can spread differently when species gather around shrinking water sources. These factors leave little recognizable trace in fossil assemblages, but extinction rarely obeys the categories preserved most clearly in bone and stone. Reproduction may have created additional limits. The developmental schedule of Paranthropus is not fully known. but any large-bodied primate with dependent young faces slow population recovery compared with smaller, faster-breeding mammals. If food shortages reduced fertility or increased mortality, numbers could decline over generations even without a dramatic catastrophe. A lineage need not suffer constant starvation. It only needs births to remain slightly below deaths for long enough. The geography of the final fossils may eventually prove especially revealing. Eastern and southern African Paranthropus were not identical. They occupied different habitats and expressed different dietary patterns. Their disappearances may therefore have had different immediate causes. P. boisei could have been affected strongly by changes in C4-linked environments, while P. robustus faced a different combination of habitat instability, competition, and demographic stress. Grouping them under one extinction explanation may hide regional histories. What survives in the record suggests that Paranthropus did not vanish because its body suddenly stopped working. Its teeth remained effective. Its hands remained capable. Its upright locomotion remained functional. The problem may have been that the environment increasingly rewarded a form of flexibility expressed not only through anatomy, but through movement, technology, dietary substitution, and wider population networks. Homo could alter behavior within a lifetime. Paranthropus could also behave flexibly, but its survival may have remained more tightly connected to ecological systems that were becoming fragmented or unreliable. Even this interpretation must remain cautious. Fossil sampling is uneven, species boundaries are disputed, environmental records are local. The timing of technological changes does not align perfectly with biological disappearances. No single explanation fully accounts for the extinction, and it is possible that several weak pressures combined into a result none could have produced alone. Paranthropus therefore leaves the story not as an obvious failure, but as a successful lineage gradually overtaken by conditions it could no longer absorb. Its disappearance was probably quiet. One population declined near a shrinking wetland. Another persisted in a better watered basin. Some groups may have survived long after others were gone. Eventually there were too few connected populations, too few reliable refuges, or too many difficult seasons in succession. The last Paranthropus did not know it was lost. It moved through a landscape still inhabited by familiar plants, predators, and other hominins. Its body carried adaptations shaped by countless successful ancestors. Nothing about that body announced extinction. Only later, when the fossils ended and no descendants remained, would the lineage appear to have reached an inevitable conclusion. In its own time, the ending was simply another season, followed by fewer tracks returning to the water. Homo did not endure because it possessed one perfect adaptation. It endured because its survival strategy became increasingly difficult to reduce to any single part of the body. Teeth mattered, but so did stone. Legs mattered, but so did memory. Brain size mattered, but only when supported by enough food, social learning, and repeated cooperation. The lineages grouped under early Homo were themselves uneven, vulnerable, and often short-lived. Yet some populations gradually assembled a combination of traits that could be rearranged when environments changed. Their advantage was not invincibility. It was the existence of alternatives. Mobility was one of those alternatives. A population able to travel farther could connect resources that no longer existed close together. Water might lie in one direction, stone in another, and reliable plant food somewhere else entirely. Long legs and an efficient terrestrial stride reduced the cost of moving between them, but the body alone could not make distance safe. Routes had to be remembered. Seasonal changes had to be anticipated. Groups needed to know when a familiar spring would fail, where shade remained during the hottest hours, and which valley still supported animals after drought had emptied the plains. This growing dependence on movement transformed the landscape from a collection of isolated feeding sites into a network. A carcass could be processed far from raw stone if useful tools were carried. Food could be transported away from danger. A group could abandon a declining wetland before every resource disappeared. Wider ranging also allowed populations to expand during favorable periods and retreat when conditions worsened. Such flexibility did not prevent local extinction, but it increased the chance that another population survived elsewhere. Dietary breadth provided a second layer of protection. Early Homo did not rely on one ideal food. Plant resources remained fundamental, while animal tissue, marrow, seeds, roots, fruits, and other foods could be combined in proportions that shifted with season and place. The importance of this strategy lies not in consuming everything, but in being able to substitute. When one resource declined, another could temporarily support the group. When unfamiliar landscapes offered different plants and animals, old processing methods could be applied in new ways. Stone tools expanded the value of that flexibility. A flake could cut flesh, slice a stem, strip bark, shape wood, or open a tough plant surface. A hammerstone could break bone, crush seeds, or pound underground storage organs. Acheulean hand axes added another durable form, but the continued use of simple flakes shows that technological success did not depend on constant complexity. Homo erectus at Engedi combined larger cutting tools with older one-like strategies under dry and unstable conditions. The toolkit remained varied because the problems remained varied. This ability to choose among methods may have mattered more than the invention of any one tool. A group faced with poor quality stone could alter reduction techniques. A group moving far from a source could carry selected pieces. A tool could be resharpened, abandoned, or replaced depending on need. Technology became a flexible layer between anatomy and environment. Instead of waiting for teeth, hands, or digestive systems to change across generations, behavior could be adjusted within a lifetime. The shift was powerful, but it was not automatic. Every technological tradition had to be learned. Young individuals needed repeated exposure to stone selection, striking angles, cutting motions, safe carcass processing, and the location of raw materials. Failed attempts consumed time and could damage fingers or waste stone. Skill survived only when individuals tolerated one another closely enough for observation and practice. Social life, therefore, became part of the technological system. Cooperation may also have reduced individual risk. Several adults could watch for predators while others processed food. Groups could move together between water sources, defend access temporarily, or recover from the loss of one skilled individual more effectively than solitary foragers. Food transport and sharing remained difficult to demonstrate directly, but even limited distribution of resources would help stabilize a group when acquisition was uneven. One individual might locate a carcass while another found plant foods. A successful strategy did not require equal sharing in a modern moral sense. It required enough tolerance and exchange to keep the group functioning. Social bonds could also support survival during injury, illness, or temporary weakness. The fossil record occasionally preserves individuals who lived long enough with severe dental loss or physical impairment to suggest that they continued receiving food or protection. Though interpretations remain debated, such cases become clearer in later Homo, but the foundation may have developed earlier. A lineage increasingly dependent on knowledge benefited from keeping experienced individuals alive. Memory itself became a resource. The brain of Homo erectus was still far smaller than that of modern humans, and nothing in the evidence requires modern language or symbolic thought. Yet modest increases in neural capacity could support improved spatial memory, attention, social recognition, and behavioral sequencing. A larger brain did not create flexibility by itself. It worked within a system that included hands, eyes, feet, food, tools, and other group members. Its value came from integration. The environments near 1 million years ago tested that integration severely. At Ngaji Nanyori, Homo erectus occupied a landscape reconstructed as semi-arid to steppe desert, with unstable vegetation and limited water. This was not the comfortable savanna once imagined as the natural home of early humans. It was a demanding setting where resources could become widely separated and seasonal uncertainty was high. Archaeological remains indicate repeated use of the area rather than one accidental visit. That persistence is one of the strongest signs of an emerging generalist strategy. Homo erectus could remain where no single anatomical specialization guaranteed survival. Powerful jaws alone could not solve water scarcity. Long legs alone could not provide calories. Hand axes alone could not identify edible plants. Success depended on combining mobility, ecological knowledge, multiple tool types, broad feeding behavior, and social learning. Each part compensated for limits in the others. Even dispersal beyond Africa may have emerged from this same combination, rather than from a special migratory instinct. The first populations to enter Eurasia were not fully modern in body or brain. Their tools remained relatively simple. Their achievement was not technological perfection, but the ability to carry practical behaviors into unfamiliar landscapes. They adjusted rather than arriving already adapted. Chance remained essential. A drought could eliminate one population while sparing another only a few valleys away. Volcanic eruptions could destroy habitats but also redirect animals and expose useful stone. A small group might fail because several reproductive adults died in succession. Another might expand because rainfall opened a corridor at the right moment. Homo endured as a lineage even though many Homo populations and branches did not. The survivors can make the strategy look more reliable than it felt to those living through it. The phrase "the first real humans" is sometimes applied to Homo erectus because the body becomes more familiar. The range expands, and technology appears more deeply woven into survival. As a storytelling image, it captures something important, but scientifically it must remain qualified. There was no single threshold. Homo habilis already carried some parts of the pattern. Earlier hominins could manipulate tools and move through varied habitats. Homo erectus added and reorganized traits rather than appearing as a completed design. What distinguished the enduring populations was not that they had escaped evolution's uncertainty. It was that they increasingly carried several responses to uncertainty at once. When one food disappeared, another might be processed. When a local habitat failed, movement could connect a new one. When raw material changed, tools could be adapted. When individuals lacked knowledge, others could demonstrate it. The survival system became distributed across bodies, objects, landscapes, and relationships. Paranthropus also possessed flexibility, social learning, and capable hands. Its disappearance cannot be explained by denying those qualities. The difference may have been cumulative and statistical rather than absolute. Homo populations had slightly more ways to respond, slightly broader networks, slightly greater mobility, or slightly more dependence on transferable behaviors, across one dry season, such differences might mean little. Across hundreds of thousands of years, they could shape which populations repeatedly recovered and which became increasingly isolated. By the time Paranthropus fades, Homo erectus is not triumphant in any conscious sense. It is still exposed to predators, hunger, injury, drought, and local extinction. Its technology remains limited. Its social world is largely invisible. Yet its range has widened. Its ecological tolerance has deepened. And its survival depends less on one landscape remaining familiar. That may be the most consequential change of all. Homo did not become independent of the environment. It became increasingly able to carry adaptable pieces of one environment into the next. The disappearance of Paranthropus did not leave the world empty. Homo erectus continued to spread, adapt, and diversify, carrying forward the long experiment in mobility, technology, and ecological flexibility. Yet the vanished branch did not simply become irrelevant. Its fossils remain among the clearest reminders that human evolution was never a straight ascent toward the present. Paranthropus was not an unfinished human, not a failed version of Homo, and not a creature waiting to be replaced. It was a successful lineage with its own history, its own solutions, and its own long period of survival. For more than 1 million years, Paranthropus occupied African landscapes that changed repeatedly around it. It endured lake expansions and contractions, shifts in rainfall, changing plant communities, volcanic disturbance, competition from other animals, and the presence of several hominin lineages. Its geographic range was broader than once believed. Its diet was more complicated than the old nutcracker image suggested. Its hands were capable of strong, controlled grasping. Its feet carried it upright across the same ground used by Homo erectus. The evidence remains incomplete, but what survives no longer supports the image of an evolutionary dead end defined only by massive teeth. Its extinction therefore reveals less about weakness than about contingency. A lineage can be well adapted and still disappear. A body can function effectively for hundreds of thousands of generations and still encounter a combination of environmental changes, population fragmentation, and ecological pressure that it cannot absorb. Evolution does not preserve every successful design. It preserves only those whose populations continue reproducing through each new set of conditions, including conditions no ancestor could have anticipated. Homo endured, but not because every Homo population succeeded. Many groups disappeared without leaving descendants. Some dispersals ended, some regional populations became isolated, entire branches of the genus would later vanish, including forms that possessed larger brains, more elaborate tools, or bodies even more familiar than those of Homo erectus. The survival of one line toward Homo sapiens can create the illusion that the outcome was inevitable. The fossil record shows otherwise. At almost every stage, several possibilities existed, and most of them eventually closed. Paranthropus also complicates the meaning of technology. The earliest Oldwin tools cannot be assigned securely to Homo alone. Paranthropus' teeth at Nyanga and the anatomy of the Boise hand leave open the possibility that robust hominins used or even made stone tools. If they did, technology was not the exclusive inheritance of the lineage that survived. It was part of a broader behavioral world in which several hominins may have manipulated stone, wood, plants, bone, and food in ways that overlapped. This possibility changes the old contrast between jaws and tools. Paranthropus carried extraordinary processing power in its skull, but that did not prevent external processing. Homo increasingly relied on objects, but it never stopped depending on teeth, hands, and bodies. The two strategies were not mutually exclusive. They differed in emphasis, frequency, and perhaps in how deeply learned technology became woven into survival. The eventual disappearance of Paranthropus did not prove that tools always defeat anatomy. It showed that a more portable and combinable survival system may have offered wider options as environments became increasingly unstable. The stone record offers no moment of triumph. There is no abrupt technological break when Paranthropus vanishes. Older one-like flakes continue. Acheulean tools remain part of a mixed technological landscape. Homo erectus does not suddenly invent a new object at the exact point when another lineage disappears. This absence is important. It suggests that extinction unfolded through slow ecological and demographic processes rather than one decisive breakthrough. The final legacy of Paranthropus lies partly in the questions it forces scientists to ask. How should a species be defined when fossils are scarce and variation is broad? How much behavior can be inferred from a hand, a tooth, or a footprint? When does anatomical capacity become habitual cultural practice? How does a lineage survive for more than 1 million years and then vanish without an obvious catastrophe? Scholars still debate each of these problems, and new discoveries continue to rearrange the answers. The changing picture also warns against allowing names to become stories too quickly. Homo habilis was called handy before the oldest tools were known. Paranthropus boisei was called nutcracker man before its toothware and chemistry were fully understood. Homo erectus was portrayed as the first complete traveller, before Dmanisi showed that smaller, more primitive populations could disperse far beyond Africa. Each label captured part of the evidence and then hardened into a narrative. Fossils have repeatedly broken those narratives open. Around 1 million years ago, no observer could have known which branch would matter to the distant future. Paranthropus still represented a lineage shaped by deep evolutionary success. Homo erectus was widespread, but survival remained uncertain. Neither possessed a map of what came next. There was no destination called humanity waiting ahead. There were only bodies moving through landscapes, groups responding to hunger and weather, and traditions continuing when one generation successfully learned from another. The branch that left no descendants still belongs to the human story because ancestry is not the only measure of significance. Extinct relatives reveal alternatives that once existed. They show that upright walking, dexterous hands, social learning, dietary flexibility, and perhaps tool use were distributed across more than one lineage. Features later treated as uniquely human emerged within a wider evolutionary community. The path toward modern humans was not created in isolation. Paranthropus also changes how success should be judged. If success means surviving long enough to become an ancestor of modern people, then almost every species that ever lived was a failure. If success means occupying varied habitats, reproducing across immense spans of time, and evolving a durable response to demanding environments, then Paranthropus was remarkably successful. Its disappearance does not erase that history. What may have separated the surviving Homo populations was the growing ability to shift the location of adaptation. Paranthropus carried much of its ecological solution in inherited anatomy. Homo increasingly distributed adaptation across anatomy, tools, movement, memory, and social learning. Genetic change remained important, but behavior could respond faster than bone. A new stone source could be learned. A route to water could be remembered. A different food could be processed. a tool could be copied. These responses could pass through populations without waiting for a new jaw or limb to evolve. That flexibility would eventually become one of the defining patterns of later human history, though never a guarantee of wisdom or survival. Humans would enter deserts, forests, cold grasslands, coasts, islands, and high mountains. They would build technologies far beyond anything known to Homo erectus. Yet the foundation was laid through modest acts repeated across deep time, carrying useful stone, movers between scattered resources, learner from companions, and combining several imperfect solutions rather than relying on one perfect one. The world of Paranthropus and early Homo therefore ends without a clear victor. One lineage disappears, another continues, but the continuing branch carries traces of a shared past in which boundaries were uncertain and possibilities remained open. The mud at Kubifora preserves two kinds of feet on one lakeshore. The stones at Nyanga preserve work without a known worker. The jaw from afar stretches a vanished lineage across a wider map. The partial skeleton of Homo habilis reveals that the road toward a familiar human body was slower and stranger than older stories allowed. As the record moves beyond 1 million years ago, Paranthropus recedes into silence, while Homo erectus continues across Africa and Eurasia. New populations emerge, others vanish. Tools change gradually. Bodies change unevenly. The future remains unwritten. What survives is not a clean handover between an obsolete creature and a superior human, but the fading of one durable experiment beside the continuation of another. And then the scale of time begins to soften the differences. The lakes fill and empty again. Ash settles over old paths. Grass returns to ground that once held footprints, then gives way to dust. Bones sink into sediment. Stone edges dull beneath soil. The individuals themselves disappear long before their lineages do, and their daily fears, attachments, habits, and remembered places vanish almost completely. Only fragments remain. A tooth carries the chemistry of childhood rain. A footstep records the pressure of one body for a moment before the mud hardens. A flake preserves the direction of a strike delivered by a hand whose species may never be known. A jaw reveals years of chewing, but not the taste of the food. These are small survivals against an enormous silence. Paranthropus leaves no known descendants, but absence is not nothing. Its vanished form widens the meaning of the human past. It reminds us that other ways of being intelligent, social, upright, and adaptable once moved through the same landscapes as our ancestors. Their lives were not rehearsals for ours. They were complete lives within worlds that mattered to them. Far in the future, another human lineage would look back and arrange these fragments into names, dates, and branches. The arrangement would change whenever a new fossil emerged from stone. Certainty would retreat, then return in a different shape. Perhaps that is the most honest legacy of this ancient crossroads, not a lesson about inevitable progress, but an invitation to remain humble before what time has erased. The last image is not a battle or a final collapse. It is a quiet shoreline under a pale sky. Water touches the mud. Reeds move in the wind. Two sets of tracks cross the open ground, made by different bodies sharing one world. One path fades sooner. The other continues beyond the edge of the preserved surface. Neither track knows where it leads, and for a moment, before the sediment closes over them, both are simply present,